history of physics. That's a video series.
We're live now, by the way.
Yeah, we are going to go.
We are live on the thing.
But we may do like once a month or something, that one. But the other times, so the the history of physics, we do want to do about 10 episodes. That will go about 6 months. So each episode will be once a month or something like that. But the other times we have special presentation, like Christopher presented last time about his anamorphic universe model, and then we'll have general discussion and other presentations in the other one. Like Christian, you may present something, or Emmanuel may present something, or Gerd may present something. So that's the third one. And the fourth one is where we just talk about Q&A, debates, general discussion. So we have these 4 different, sessions, you can say.
Yeah,
different types of sessions. Yeah. So that's the main aspect. And today, I thought that I'm going to present the history of physics, episode 1, which is a repetition of last time. But last time was just introduction to that, and also a preview of that. So today we go into little more details. And let me mention that the history is such a vast area, but it's very important. And so we are just concentrating on certain sections. We are not going to concentrate too much on the technical aspects. But we will emphasize certain critical aspects. Like my presentation will be a very short one, like half an hour, 1 hour the most. After that, we had excellent discussion with Christopher last time, the first one. You should watch that, because after that we discussed the fact that how it came to being, because there are a lot of religious things. So we eventually will do the history. After that, we'll do how the religion, physics came into being, politics and physics came into being, and also how philosophy and physics came into being.
Yes.
So, and there may be one more thing, like.
Okay. So Rajan, do you want to start then?
Yeah, I will start now. Let me put a presentation. And
we're already live. I don't know if I mentioned that, but well, I did try. I don't know if you picked up on it.
Yeah. So what I'm going to do, this is where I'm going to do. So I'll be concentrating. I'll be going off screen. So you will see only my presentation, because I had to go full screen. So essentially, I'll put a presentation, and then essentially you will see, and only my audio will be there. Okay.
What you did with your audio is now crisp, clear. Is much better than the last I had in Remember from the microphone perspective. It's very good.
Oh, it's clear. Oh, thank you.
Yeah. It is.
So let me. Can I start now? Okay. So let me go full screen. I think you will be seeing only my screen, and then my talk. Okay. So let me go. Okay. All right. So I hope you can hear me. You can always.
Rajan, can you make that a full screen?
Is not full now? Let me check.
But you need to present it. I mean, just present the. The slideshow.
Okay, so let me see.
Also, Rajan, this looks to be the exact same talk that you gave last week.
Well, I'm just continuing on that. I added on to that so that even if you miss
so
the first
I've already technically seen this talk, and we already actually have this.
No, yeah, but I'm going to expand on that. See, let me see. Okay. I want to go full screen.
Yeah.
Let me try to go full screen.
Can you maybe remove the elements of the presentation tool itself in a real presentation mode? It takes more screen estate than the small characters of the actual presentation.
Okay, so let me see.
That's what I'm getting at.
Let me see whether I can. If I go from beginning. So I don't know why it doesn't. Okay.
It's weird the way it changes size like that.
Oh, only the side one.
You need to
Windows enters from my point of view on the
start slideshow.
From 16 to 9 point of view, we lose a lot of black left and right of it.
Yeah, that's better. and then just click present slideshow, or you see down by the bottom of the screen with the slider that makes things bigger and smaller.
Yeah, maybe.
Yeah, don't touch that. Don't touch it, but go to the left of it. Go just to the left of that slider that you were at, and click that button, that one, yeah.
Slideshow, okay.
Yeah. Okay, so there must be, that's strange, isn't it?
Yeah, a bit strange.
Yeah.
Why does that happen?
Yeah, that's what
I can read it. It's big enough from my screen point of view. If it's big enough for the transmission of live on a YouTube video, I'm not sure. So you have to decide if you scale in or continue with that way. From my point of view, it's okay.
Yeah, this is fine, Rajan. If you want to go with this aspect,
okay.
I think it's probably best.
See if I can reduce this part of it. I think reduce it a lot more, and then go like you mentioned, see whether it will reduce. No, I should be able to remove this one, I think. Somehow. No,
normally it would do that automatic with the ribbons away.
Yeah.
Yeah, I know.
I thought last time it was doing that.
Well, maybe we could, maybe there's some setting or something that you need to apply.
Yeah.
Or maybe there's some setting. There you go. That's better. Let's go with that.
Let's do it this way. This is good.
Yeah.
This is good? Okay. Setup slideshow. There is something.
Ignore it. Just start. This is just
okay.
Fine.
Just start. Okay, it's fine. Okay. So we'll go with this one. I'll just go slide. Okay. So this works, right? Okay. So I just want to ensure that when I move, okay. All right. So if I go, oh, it doesn't move along with that when I move this. That's what I want to find out. Why it doesn't.
I think this is some Windows problem. It has nothing to do with nothing. This is just a bug.
Okay. So I want to ensure. Ah, that's strange. Okay, let me see. Why it doesn't move along with that.
Don't worry too much. Roll ahead, and I think
yeah,
he's all good from visibility point of view.
Ah.
Can you change the slides, Rajan?
Yeah, that's what I'm trying to do. When I'm moving, it's not moving there.
Okay. That's not good.
Yeah, that's the one I am trying to see. So why is it not doing that? Let me go back to a presentation. Oh, I probably will get off the presentation and then redo it. You know what I mean? I'll stop it and then do it again. That might do the trick. Sometimes
okay,
that's good. Yeah. So I think I think it should work.
Unfortunately, the JavaScript-based world has imposed a lot of additional dependencies to these kind of full screen things, because today nobody...
now it's moving. Now it's moving. Good.
Yeah, that is...
Yeah. So that's now it should work.
Oh, this is a completely different thing. You could even try clicking on the...
and now it should work, actually.
Yeah, start slideshow. Yeah.
Let's see whether that doesn't work. That's
try it again. There's a different
the other one.
Let's try and view full screen if there's a full screen menu under view, because you're operating currently always from slideshow, but on the right, the second from the right menu next to help is a view menu, and it could be that view menu contains in the ribbons a true full screen in the sense of menus away.
Have you tried clicking that button at the bottom of the screen with where the slider is?
Yeah, I think it.
Yeah, that's what I'm trying to do.
Jumps to the square area with a lot of black in between.
Oh yeah, but he seems to have advanced from that. So because now you even have a different slideshow up, which is weird.
Yeah. So let me. I think this one is the only one that works.
Okay. Whichever one works the best.
Oh, yeah. Now it's working. Okay. This should work.
Great.
All right. Okay. So, okay. Essentially, this is a continuation of last show about that was about 2 weeks ago. That was on February 10th, 2024. We started talking about the history of physics, and that was an introduction, and we had a lot of information about that, how the history of physics connected with what happened before. Today it will be more specific talk about the episode 1, and we talk about what really led to classical physics, and then we'll also preview the episode 2. So we want to continue the understanding of the history of physics. We are not talking, so we take away from the religion. We are not talking about that. We won't be talking about the politics. That will be a separate topic, and philosophy. We eventually plan to have a world university where we start with the philosophy, physics, etc., in the auditorium, and the info room, which will be a presentation room where we start the history of physics, and we hope to have this as a material for that, and then eventually we'll have like 10 episodes, and then we hope to make a movie, such as a documentary movie that Christopher was suggesting. So that will be after 6 months or so, 6 to months or 1 year. So this is the first aspect is the what was the one before that, and that's a very dicey situation, in the sense that we don't get a complete picture of what was going on before, but we only know that the Copernican revolution changed the geocentric model, and that we talked about last time. So this slide is only a repetition of the preview, and so I'll be going into detail about that. And then Galileo have advanced the telescope, which was there before, but then he advanced it. And Johannes Kepler, who was assistant of Brahe, also did a lot of work on understanding planetary motion. Then it was Bacon and Descartes who did the methodology, how to do the scientific exploration. And then Newton came, and he started establishing the mechanics of the universe based on the gravity that Galileo had experimentally showed. Then we continue with Franklin and Volta and Faraday and Maxwell. They describe the electromagnetic field, how they are connected with the light to be an electromagnetic field. So electricity and magnetism were studied in detail. Then we have the thermodynamics on the side that many people developed, and they found, and that formed the basis for understanding energy and the conservation of energy, and then entropy, and also what we use that now for temperature. We won't go into detail about the technical aspects, but we'll emphasize how the history led to what we have present day of the quantum physics as well as the relativistic physics, and now we are trying to combine the standard model, and there are problems with that. We'll be going over in subsequent episodes about that. So astronomy was one of the main attractions of all the people, and people in the night sky, if you look at the night sky, you see a twinkling star, and then even for babies you talk about twinkling stars. So that's what we see. So the observation physics is very important. Let me emphasize the observation physics. Essentially, we'll have observational theory and experimental physical sciences, which means that whatever we develop has to somehow make sense what we see. And that's the whole thing. We see that twinkling star, but we wonder what is beyond that. Beyond Earth is something on. And this is what, engaged a lot of astronomers, and they started, even earlier days, instrumentation, they started doing that, especially what we call a telescope these days. So we can peer into the beyond the sky and see what's going on there. And it has to be, they also realize it has to be complemented with some kind of understanding of the theory behind that, conjectures, this or that, and then test them. Geocentricity was one of the earlier form that the geocentric model was developed by Aristotle, I should put Aristotle, BCE, and then Ptolemy, Christian era or AD, you can say, that we'll be discussing that, more probably in the religion and philosophy, other speaks. And also our discussions will concentrate perhaps a little bit on the Christian era versus AD and BCE, before the Christian era, things like that. But essentially what it was that they considered the Earth to be the center of the universe. And still there are a lot of scientists, even scientists, believe that actually Earth should be the center of the universe. And the sun, moon, and the planets are revolving around it. But Copernicus, in the 15th century, thereabout, argued that sun should be the center of the universe and the solar system. And then other planets, such as Earth, should be revolving in circular motions. And that the Earth itself rotates for about 24 hours. And the Copernicus model was much simpler, whereas the Ptolemaic and the Aristotle model, they had epicycles and other things to explain the aspects. And so Copernicus simplified, and they could solve the retrograde motion of the planet. So that was one of the big problems, the retrograde motion of the planets. Again, and I'm going to go into details about that, because that will take up. That's a separate lesson by itself, and you have standard lessons in the universities and the books that talk about that. We are just going to mention how the history developed to the present day modern physics. Then Brahe, in the close to 16th century, and Kepler, who was his assistant, and then Galileo, and then Newton started using the astronomy to develop the laws of planetary motion. So they measured very accurately the orbits and their relationship with the geometry, and they found a lot of relationship. And they used telescope a lot, especially Kepler, and Galileo also started using that. And Newton, to some degree, Newton was more in the theoretical aspect, but also he used the astronomy, the telescopic astronomy. And he developed eventually the universal gravitation that we know about, the capital G, which is called universal gravitation constant, which describe all the heavenly, they used to call them as heavenly bodies, or the astro objects, or the planetary motion, and the systems like solar system, generally star systems and galaxy and beyond. Brahe showed that comets and the new stars were celestial phenomena and not atmospheric ones. So this is one of the things he kind of clarified, that it's not just as atmospheric from the Earth, because what we see in the night sky is that we think that it's atmosphere. But what we see, actually, the stars are much beyond that. That's what eventually led to the understanding that there is an air, that's surrounding us, and that formed the atmosphere. Somebody came in. Okay. All right. So that was the main aspect that we talked about, and then essentially that led to the understanding that the comets, and so they study each of the heavenly bodies. We call heavenly bodies, which consist of stars, the planets, the comets, the satellites, things like that. So Johannes Club want to quantify that. So all the observations put together, and he said that the orbits are not circular; they are elliptical. And he stated that the planets move much faster when they are closer to the sun and slower when they are further away. And the second law stated that if you join a line between a planet and sun, they'll sweep out equal areas, and that form very, very critical geometrical relationships that help later on to find the periods of the, all the planets and the stars and all that. And the third law says that the square of the orbital period is proportional to the cube of the mean distance. Very, very important quantified relationship. And that helped later on to people to understand all these in a quantitative physics manner. So we talk again, but the gravity, forces, optics, and mechanics of the classical physics. So Galileo, it is the experimental gravity, as I meant, we talked about the last time, that he dropped various objects of various masses from the Leaning Tower of Pisa, and he found a common relationship in the sense that all of them fall at the same time. So that was a very revealing understanding of a force that is acting, a virtual force. I call it gravity, that is centrosymmetric, that's pulling everything to the center of the Earth. So that experiment was repeated many, many times in different ways, and he showed with the horizontal experiments as well as vertical experiments that indeed, if you throw something up, it comes down. So we still are trying to understand that gravity aspect. Is it a real force? Is it a primary force? Things like that. We'll talk about that in further episodes. But he also improved a telescope, and he observed the night sky. He discovered craters and moons and the mountains on the moon, the faces of Venus, the 4 largest moons of the Jupiter, the rings of Saturn, the sunspots, the stars of the Milky Way. Excuse me. So, thus he formulated the laws of motion and the inertia, which describe how objects move in the absence of external forces. So Isaac Newton originated the law of motion, and he showed that yes, he developed from Galileo. So Galileo laid the foundation for the physics. He formulated the laws of motion, which means the equation of motion. Very important. The distance, how to measure the distances with the rulers, and then the time, then find the speed based on that. Very simple things. And then acceleration, which is rate of change of the speed, and then later on it was called the velocity and acceleration, which were vector quantities, because it depended on the direction of motion. And so very simple things, and he found interrelationship between them. And by measuring just, for example, the time of fall, you can measure how much distance it has covered, things like that. And then he came up, based on that, came up with the understanding of the gravity, and calculated the small g, which is the acceleration due to gravity of the Earth, and that was considered as 9.8 meters per second. So these forms fundamental constants also. And then Galileo said that the object of the motion, depending on the direction at which an object is launched, we can have different geometry. The trajectory can vary according to that. So that helped to understand, not only the objects that move on Earth, but also the astro objects. And then he came up with the understanding of principle inertia that eventually formed the first law of Newton's physics. So the inertia essentially is where there is no external force applied. So they have to distinguish between the gravity. At that time, they distinguished between gravity and acceleration without the gravity, which we may call it an horizontal force. So if you have a very large object, we try to push it. It's a very large object. It has inertia. It will resist the motion. And that's one of the bases for the inertia that he found. So there are a lot of observations, very critical, very simple, but very profound observations that help and assigned every other scientist, either their disciples, pupils, assistants, associates, we can call it, and scientists all over the world started taking notice of that, and they published it. And that formed the basis for the development of the classical physics. The Isaac Newton, he originally a lot of about the he expounded and expanded on Galileo's work, and he came up with the universal gravitation, and he showed that every mass in the universe attracts every other mass with a force proportional to their masses. So he developed that not only the Earth is pulling it, but each mass, pulling the other mass. It's very, very, extended, very clever way and very profound way of understanding gravity. But of course, it was difficult to prove that aspect. Even now, today, the masses, how the masses attract each other with gravity is really a very difficult conundrum for many of the physicists. Nevertheless, using that, he said that attraction should be proportional to masses and inversely proportional to the square of the distance between them. It's a very simple understanding. And he used this to explain the motion of planets, tides, comets, other phenomena. And as we know, one of the things I want to point out and I'm looking into is something called Halley's Comet. The Halley's Comet is a very, very regular thing that comes probably about 76 years or so. And that is a proof of many of the scientists, and they are being recognized because of this particular phenomena that nature is really. And later on, we talk about the time loop, things like that, that I talked with Christopher also, that it is maybe related to the Halley's Comet because it's about 80 years. But that's much later. So Newton then developed the three laws of motion. He said that principle of inertia, he said that, as we know the law that any body will retain its position, and then if it's moving, it will retain that position unless it's changed by the force. So that inertia becomes the fundamental property of matter, what they call matter. Then the force, he calculated force as mass times acceleration. Again, I developed that the mass, and we talked about the mass and the weight are different things. Mass is the amount of matter contained in a body. And if you take from here to moon, for example, the mass doesn't change. But the weight is dependent on the force of gravity, acceleration. So that acceleration, if you are doing horizontally, for example, if you move an object and then we keep pushing it and change the velocity or the speed of that, that's acceleration. That requires a force. So the force is directly proportional to the mass as well as to the acceleration. And then the third law, he said that every reaction should have an equal and opposite reaction. And eventually, as we know, the rocketry and other scientists, other physics aspect developed from that. And then we see that application in everyday life. And so he came up with the mathematical relationship that quantified physics. He also showed, Newton also was quite interested in optics, and he wanted to connect all this together with the corpuscular theory, things like that. But very important contribution, he said that the white light, you can actually decompose and you can get the colors. All the colors I call with geode, the violet, indigo, blue, green, yellow, orange, and red. and we can combine them or separate them using prisms and things like that. So then he explained about atmospheric phenomena, why we see rainbow and all that based on that. So these are very excellent contributions that could be verified mesoscopically. I call mesoscopically mesoscopy in the sense that what we observe normally with our eyes and ears, and then we hear from ears. So that forms the fundamental basis, because we can always question about the instruments that's developed, and then we measure them, and there could be a spuriousness based on that. And that's, when you talk about quantum mechanics, we'll be emphasizing about that. Okay, so this classical mechanics that developed by Galileo and Newton primarily, based on the previous work by all the scientists I mentioned earlier, led to the understanding that there is another force, there is something more, and that's electricity, magnetism, and the interrelationship that help to create machines or devices that we use even today. And this is a very important part of the Industrial Revolution, which develop machines that will, complement or help people, and also sometimes replace people in very hard jobs. So Benjamin Franklin was the 18th century. He was an American polymath in the sense that he had knowledge of many different subjects, not just one subject. But he did an experiment on kite and then showed that lighting is a form of electricity. And he invented a lighting rod, which is used everywhere in all the homes, all the establishments or structures, to prevent, even for trees, destruction by lightning. And he introduced also terms of positive and negative charge, which is used now in many of the most of the developments of physics, electromagnetism, even everywhere, that no intervention said there's a symmetry, and that symmetry is based on the positive and negative charge, etc. Then Coulomb, the late 18th century, close to 18th century, developed his law about the electrostatic force of attraction and repulsion, very important. And we know, again, that's very similar to gravity, so that's why many people now think gravity is just also electrostatic or electricity. There's a connection between that. We'll be talking more about that later on, because very similar thing, equations apply there. And then we have epsilon and all that, and then inverse of r square and r cube, depending on whether attraction or repulsion. And he also studied about the friction and torsion, very important part. Friction is something has become, the horizontal force. One of the aspects of inertia, sometimes we confuse with the friction, but inertia is separate by itself. Even if you are on ice, if you push it, it'll keep going, because there's almost zero friction in there. And only in, totally devoid of air and everything, you will have zero friction. Again, that's another topic you can consider. But very low friction almost, so it can keep moving without applying any force. So but most of the objects on Earth have friction. Whenever you move, it's going to resist at the surface, the forces between the surface. And there's intermolecular forces, things like that is locking in, creating friction. The torsion, as well as if you bend any object, that undergoes torsion under twist and different types of forces. Then Volta, he developed with the battery. So he said that, as we know, in the Industrial Revolution, power was very important. So people started developing power in many different ways. And then Volta said that you can actually create from electrochemical reactions that I studied a lot, more on the corrosion aspects, the materials and the degradation, which is electrochemical in nature, by the way. And he developed battery. So you can use, you can get a steady electric current using Volta pile, which you connect the positive to the negative and then create a whole chain of batteries. And that way you can get more and more. And that's used all the equipments and devices now, including the computers, the way you use. And he defined the electric potential in terms of the measurement, in terms of the unit of volts, which is used heavily in all the developments. And ampere related the magnetic force of the two carrying wires. So ampere said that, some of the people I have put the first names, and ampere and Gauss I have not put the first name. We can actually add that if you want to. But again, the 18th, later part of 17th century, 18th, early part of 18th century to 19th century, Ampere also developed understanding that if there is two wires that carry electricity, because by the time they started understanding about electricity, that we move, the structure of the atom was not fully known. And that's something I also emphasized last time, that Dalton said that the atoms are the smallest element, you cannot break any further. But Rutherford showed indeed you can. And he showed with his measurement alpha and alpha rays and things like that, there is something very heavy in the middle. We call it nucleus. And there's something around that, it's moving around. Eventually, they found that it's electrons. These electrons can be moved by the potential, the potential that we talk about here, that Alta talked about. So if we connect with the conducting wire, we can actually move the electricity through that. And then there are two wires parallel to each other. Then there's it can either attract or repel depending on the direction in which the electricity is, the current is moving. So he developed eventually his Ampere's circuitous law that said magnetic field around a closed loop is proportional to electric current. That formed the fundamental basis for all the induction aspects, and including motors and other things that developed later on, and dynamo, the power sources. Gauss, again, in the 18th century, or thereabout, a little later, closer to 19th century, again said that the electric flux through a closed surface is equal to the net charge enclosed by it. That's how we started quantifying physics. Mathematics started becoming a very important part of physics. Until then, it was more qualitative, more philosophical, but now the math started going into, detail, and then we'll talk about later on that the standard model, the math started almost detaching from the reality, and that became a little bit problem for physics later on. But in any case, these are very important, simple laws, simple formulae that is applied in developing all the instruments, devices, and other machines and things like that. Its law of magnetic flux states that magnetic flux through a closed surface is zero. Again, that's very important to develop, including the CERN and everything, that we need to know these kinds of constitutive equations, and how they are conserved, how the energy is conserved, things like that. And that helps us to understand many of the bases for the geometry as well as the interactive aspects among objects that are electricity. And as we know, the structure of atom, now we are electrons, so that electron aspect cannot be any more neglected. And that could be, and the electron is moving around, so it creates magnetic force, things like that. So we have to see, that maybe gravity is an effect of that. But that's being developed by many other scientists, including our own group, who is developing that. Many other people in our group is developing how the gravity could be explained in terms of the electromagnetism. Okay, Michael Faraday was one of the primary physicists who stands out, because he was not only a physicist but electrochemist. And when I studied electrochemistry, which was one of the main subjects for the corrosion, Faraday current was the fundamental thing on which we based. He discovered the phenomena of electromagnetic induction. So he formally developed how the electric current can be created by changing magnetic field. And as we know earlier, Coulomb and other people, Ampere and all, had developed this. But Michael Faraday did experiments that you can change a magnetic field in this case. So you can put a magnet through a coil and create an electric current, and that formed the basis of a lot of transformers later on. Changing electric field produces magnetic field also, vice versa. Okay, and that led to the invention of electric motor, electric generator, and a generator such as, I like dynamo, which is a smaller version of the generator, but all the hydroelectric projects, the electricity we get is based on this phenomena that, we flow the water from a waterfall, and we collect on turbines. When it turns up turbines, the turbines then generate electricity based on this induction process. That moving, if you change the magnetic field, then you get electricity flowing through the coil that's connected with that. That formed also the basis for transformers, which shows the interaction, and your voltage up transformer, voltage down transformer, and that's very important because transmission, you have to have minimum current flowing through that, so you don't lose energy by heat, things like that. So usually transmission is by high voltage, very high voltage transformer, and then when we have to use for equipment, we have to step down the voltage. So you have step down transformers. So very large development occurred. So this is the this is actually a gist or a very simple knowledge of the history, very simple sampling of the history, so to say, that I did, that led to the classical physics. So the episode 2 will concentrate more on how that, based on this classical physics, how the dynamics developed, and also Maxwell, how he used that. Because Maxwell used essentially all the, work that Coulomb and Ampere, Gauss, and other scientists did. He put them together, and he said, unified the theory of electricity, and he formulated 4 equations that still is the Bible of many other physics, of the quantitative physics or mathematical physics that we call it. And he described the electromagnetic field. His contribution essentially was the electromagnetic field propagated by electromagnetic field waves, and hence the light is a form of the electromagnetic field. That's a fundamental thing. And so he formulated that, and he found the speed of light being constant. At that time, around that time, just about after that, Michelson-Morley, measured the speed of light, and that was considered to be 3 times 10 to the power 8 meters per second. And he's from Case Western, Case Institute of Technology, where I got my master's and PhD. So that's where this the Michelson-Morley had measured the speed of light. And Maxwell came fundamental equation based on the electric permittivity and magnetic permeability. We call it epsilon naught and mu naught in vacuum. And based on that, he said that, it's inverse of square root of this epsilon naught, mu naught. That's what C is, which is speed of light. And that's constant in vacuum. Very important thing that Einstein later on used. It's called the flat space model also. But based on these, his equation, the 4 equations, which the higher level calculus, including curl and, and also the development of the field itself, how the magnetic field, the magnetic flux is related to the electric field. The electric field is connected with the magnetic field. The 4 equations talk about these relationships in a mathematical way. Okay, the curl, gradient, and so forth. And based on that, the radio waves and the X-rays were developed. So there's a interrelationship. I mean, not all the technique, what you call technologies developed from the physics, not necessarily, but the interaction. Sometimes the technology is ahead of the art, is ahead of the physics, and then the physics try to understand it. But a lot of times the physics then develop these theories, and that help the development of a new type of devices, things like that, and X-rays, radio waves, radar, for example, which was used in many of the wars, and equipment that's used even today to calculate the speed of a moving object, and we've used that to understand the motion of planets, including Doppler radar, things like that. Then Hertz was another scientist, another physicist, he's a German physicist. He confirmed Maxwell theory. So many other theories that develop, eventually has to be confirmed by experiments. I mean, that's a must, because how do you know the theory is correct otherwise? So final proof comes from the experimental aspects, I said. So close to the 19th century, then Hertz, he produced and detected electromagnetic waves in the laboratory. So the laboratory become very important part. Lab model or toy model, things like that started developing from there. So people could just do almost in their backyard, or they can develop institutes or small places where they can conduct these experiments, and then use the electromagnetic waves. And then later on, of course, laser and other aspects were developed, and understanding the light itself was a very big aspect. The theory of what you call the theory of light became the main cornerstone of physics. And then the photoelectric effect that Einstein eventually got the Nobel Prize for, because he showed instruments, devices that can convert light into electricity and electricity to light, things like that. The emission of electrons by light. Okay, that we talk about later on about the quantum aspects. One of the things I want to emphasize, and I think I did that last time also, one of the reasons that the classical physics was not sufficient was that what happens, the aspect of energy that was brought about by thermodynamics. What happens to the energy of a moving object? Is it going to absorb that energy, or is it going to radiate that energy, or give out that energy? So Einstein, for example, in relativity said that for especially the larger objects, mesoscopy, it doesn't matter. The energy compared to the actual masses is very little. So there may be friction and other things. There may be creation of heat. Or you can hardly measure temperature. But if you are highly insensitive instruments, probably you can even measure the temperature. We'll see a little hotter object when it starts moving. That's even true for us. All the moving objects, including humans and living objects even. But for particles, for small particles or atoms or subatomic particles, this becomes very important. And Einstein said that this is going to absorb the energy and increase its mass. So that was part of its relativistic theory. But the quantum mechanics said, no, moving objects actually radiate that energy, and you can actually see the radiation of energy. Hence, there should be an electromagnetic wave surrounding each object. So Broglie and other people started developing the understanding of duality, that wave and matter are interrelated. So there's a wave connected with the particle and vice versa. So they came up with the understanding of field. And Einstein didn't like too much about that, because spooky action is a distance. What is a field? Things like that became a very important topic. Even today, unified field theory is a very hard object. But Einstein tried to put them together, and we'll talk about that for episodes, how that happened. Essentially, thermodynamics was the key cornerstone. Again, key thing that even now people think that unifies, that everything has to be explained in terms of thermodynamics. So that's a science. That's a science that related the heat work, because normal situations, what we are interested in the heat, the work that's created. A lot of the instruments that we use, like even in cars, things like that, we burn from gasoline, that creates the heat that is used to run engine, right? Then we have about temperature. Temperature is what we use. We describe whether it's hot or cold based on temperature, and we measure temperature minute level, and we know 25 degrees centigrade, things like that, or 70 or 80 degree Fahrenheit. So you have different units, even centigrade, and then Fahrenheit. I'm going to go into detail about that. But then you have Kelvin temperature. It talks about absolute temperatures. So these are all developments of thermodynamics. Essentially, talks about how the transfer energy from one place to another. Eventually, they develop systems, closed system, open system, things like that, and from one form to another. So the energy can transform from the higher form of energy, what we call electromagnetic energy, is called higher forms of energy, to a lower form of energy, which is heat. So how does transforms and what happens then? The effects of the process on physical properties, how it changes the physical properties, and the entropy, what we call the second law talks about entropy, and there are a couple of more laws. So it studies the limitation of the efficiency of energy conversion direction. Like I said, I'll be talking a little more about that, Carnot cycle, things like that. And that proved about the efficiency that it has to be less than 100%. We cannot convert all of the energy into useful work. So that's what Carnot's contribution was. So that's still valid today for a lot of heat engines. It was driven by the practical need to understand and improve performance of heat engines, such as steam engines, which was developed to the main sources of power operating the Industrial Revolution. So at that time, we used coal and other aspects to actually refine metals from their ores. Like, for example, iron ore, things like that. And they use blast furnace, which is one of my areas I studied, metallurgy. And although I concentrated more on the treatment of that and also chemical, mechanical effects of that, such as even including corrosion and other aspects. But the Industrial Revolution showed a vast progress, very astronomical progress in these, using these, and then eventually created the internal combustion engines that was used to power cars, vehicles, especially automobiles and other bigger equipment, trucks, buses. And so they use heat engines. And so they have to understand some kind of simple calculations that engineers can use to develop these engines. And the main pioneers of the thermodynamics was a whole lot of people, and many of the names we don't know. So it's an anonymous field, but we know about the Carnot, Clausius. There's a Clausius-Capron equation, very important for thermodynamics. We study for thermochemistry. In chemistry, thermodynamics used extensively to find the reactions, which way the reaction is going to go. And Le Chatelier principle, which says how the pressure and temperature is pushing the reaction, the forward or reverse direction, things like that. Then Joule, who developed the unit of energy and then measurement of energy in a more precise manner. And Boltzmann, who said that there's a direct connection between the heat content and the temperature, which is the gradient of the heat. So it's simply called the energy or the heat as K times T, where K is the Boltzmann constant. And that was a very simple law that was used. But that's valid, again, many other electrochemistry everywhere. The linear law is valid around certain region. But the larger region, we have a non-linear behavior if we plot that. But Boltzmann formed. And then he stood and Stefan developed the power law, which he said that the power should be sigma times t to the power 4, the fourth power, and sigma is the constant. So again, I'm seeing that has to be used for radiation calculation. For example, you talk about Planck radiation, it should be connected with the power, and then we'll talk about that later. But that's a developing area again. The concept of entropy that developed from the understanding of thermodynamics, very important. And that entropy measures the disorder or randomness of system. We'll be going into more detail, but just want to point out that entropy, the second law said the entropy should be increasing, or the universe should be increasing. And the area of time is connected with the entropic aspects. So then we have the time, then you have the temperature, and we study something called transformation that forms the fundamental basis of the physical metallurgy, that time temperature transformation, how you can, there's a complete phase diagram and other aspects which gives what is the parameters that we need to melt some ores, and also get and how to refine them, process them, and then later on processing them, like you make into wires and things like that, how to make it pure, things like that, and that all the structures based on this understanding of time temperature transformations. Transformation essentially includes the phases of starting with the solid, liquid, gaseous phases, how they come together. So that's physical chemistry also. So these are some of the main aspects that I want to highlight. It's just a highlighting, I would say, more than going to too much detail about technical aspects, which is there in many books as well as courses, and then our own research that our group is doing and other people are doing. They go into more detail about them, and then dissect all these aspects, analyze these aspects to understand aspects. But the history is important. Why we are taking upon this project is because right now there's a problem of meshing together the quantum mechanics and the relativity. There's inconsistencies, and we know called the vacuum catastrophe or ultraviolet catastrophe. They have made it very difficult for people to accept many of the aspects of physics. And so we need to revive the physics to have faith in physics for many people. And that's why we are going to detail, go back to the blackboard. That's what we are doing, and understand the historical aspects. And some people feel that classical physics can explain all the things that quantum mechanics and also the relativistic theory if you use certain improvements on them. And one such theory is called the modified Newtonian dynamics. And there are other aspects also. Of course, there's quantum gravity in the aspects we'll be talking about. But essentially, to really put the faith back in physics and also solve them, like for quantum computing, things like that, and use them for instrumentation, and then patch up that so that we can say, how to improve for even standard model, things like that, and quantum field theory, all the aspects. We have to do some real, hardcore recalculation, rethinking, and then come up with a way. And many of our people are also doing that. Like, for example, Christopher is doing the geometric aspects, and Christine is doing about I space, and also looking at the constants, analyzing the constants. Gerd is looking at the metric universe, how that can be explained, all the astrophysical aspects. And Manuel is also talking about astrophysics. Emmanouil is talking more about how the gravitons and electrons, everything can be combined together. And then Emory, the discrete physics, and I myself, I involved with all the people, especially developing the mathematics of discrete physics, as well as fundamental theory of point physics from Helmholtz decomposition. So these are the things that's going on. And I just want to highlight some of the aspects, and we'll talk more in episode 2 and then Maxwell. So I have certain plan for each other, or we have certain plan for each of the episodes, but they will change depending on how the presentation goes, how the discussion and debates go, Q&A. They will change. So we won't be having every week. We'll have probably once or probably the maximum twice a month. We have other aspects, like I mentioned earlier, during the earlier times. We'll have this history of physics once or twice a month. Then we have special presentations. And then we'll have Q&A and discussions and things like that, and then general discussions. And also we'll have one more session where we talk about what we are going to do next, and feedback, things like that. And we hope to attract more people to be able to use our whatever we are developing here for a larger system. We hope that even school systems and college systems, other industries can use this, because I myself teach as a guest teacher in schools, found that there is no comprehensive understanding of the history, and then sometimes the students are confused about what's going on. So I think hopefully this will help that. Eventually, you want to develop a movie that will be used for everybody, scientists and non-scientists. And let me emphasize, there is no non-scientists, although we distinguish them. Everybody is a scientist in their own regime, because everybody is observing that. Sometimes we have to talk to people who are not, parochial in that field, to really understand what is being seen, because that's what we relate to, the actual observations. And we should always check our theory and everything with the actual observations. And sometimes we are biased by our own theories, and that's something something to think about, and something that all of us should take note and see how we can detach ourselves from these theories and see for ourselves what we clearly see, and able to explain what we see. And that's the fundamental basis. I mean, we see these things, but how do you explain them? And that's the fundamental aspect. So thank you very much, Talk. And then I right now I like to invite all our scientists here to talk more, and then more feedback from everybody, and based on that we'll proceed further. Thank you very much.
Yeah, thank you, Rajan, very much. That was very concise, and I'm always amazed when we see what dates are in these timelines. So within, especially the area from 1750, when you take the birth dates of these scientists and take when they are fully educated and starting to actually do scientific work on their own, typically from 1715 to 1815, in steps of 10 to 20 years, these massive steps of understanding happened in a way that must have been shaking for the people of the world. Of course, when you are struggling for your food, you probably not recognize that someone invented a battery and will not be able to imagine. But from the especially scientific full paid entities like in UK and so on, when a Volta in Italy suddenly sets the basis for experimental electrical physics by inventing the battery, that is huge, because not always you want to wait for a lightning. And
yes,
but you see that even the simple nature phenomenon of weather and lightnings, electricity in the air is present for everyone. Just I have the saying, which I really like, in a way that ideas are seeing what everybody sees and not thinking what everybody thinks. And these are the great persons of the scientific history, and who knows what we will see in our area. I think we're living in interesting times.
Yes.
I had not so much time to do physics, unfortunately, in the last couple of months. But at least when I'm waking up in the bed in the morning, so from 7 to 7:50 to get my eyes open, I really type posts to ResearchGate, and often provocative ones, intentionally provocative ones, to see what people think on harsh ideas, be they right or wrong. So I have no proper judgment that my ideas will be better than others. But what I can see is the discussion in its own involves in the thinking of the overall questions as stated in ResearchGate. And TEGS is a forum where we, unfortunately, too rare have time to do a thorough peer exchange on what we achieved or what happened. It worked well, great over the given years we are doing that now. But still there is no formalism which would let us say routinely like we're sitting in school and getting us forward in a way which other people would recognize. I mean, what we have done in the past with Emmanouil and my work together, and with what you had set the base for the whole framework of discussing this here in YouTube form. I'm not sure if the live way of talking has progressed us or if it hinders us a little bit to be cautious what to say in what area. So I had a bit the feeling that the more reducted way of a lot of work for Christopher or others, of course, had given us the freedom to really shoot out whatever you had in mind, and then still got the smoothed out presentation, which is very, very difficult. And the new rules of Christopher given over the last month, I had just a side note reading it that he has some structure for presentation. I think that is very, very good, but it shows on the other end that you have to formalize your thoughts already upfront a little bit and prepare yourself. And while that is completely a correct way of doing things, if you do scientific things, you should not mark out, yeah. But it takes much more time for the person preparing the talk, and that reduces the number of possible talks. Where I say when I'm coming from IT world, and we have a lot of chaos in IT. I mean, really chaos. This is not scientific anymore. So everyone invents not only code of new style every week and pushes it through the world. Over the internet channels, but really they invent new languages every week and pushes them to the channel. And there is nothing you could express in a new language which you could not in an older one, but just getting back a little bit and reading a few good books of history of IT and say, why do we have it done that way? It wasn't wrong all just because you didn't read all the books before you're too young. You can't understand that. So the amount of information is clearly too much. And this is what we are struggling in physics over the amount of useless information compared to the amount of useful information per paper is in a way that we can only have our own ideas, surf on and see what happens. But that is in its own way extremely productive sometimes, not really the scientific way these people have invented already in the Middle Ages. You say you go to your desk, have your experiments, and you predict from the first measurement values what you understand, make an equation, predict the next values you will do in your measurements, and so on. So everybody is sitting for 120 years now here that all the theory of relativity, all the theory of quantum mechanics, quantum electrodynamics, and quantum chromodynamics is just there. And if you want to do something better, you have to reinvent everything, or we don't listen to you. Yeah, and that obviously brings most persons nowhere, because no one is able to, in a human's lifetime, absorb all that details levels on all these theories. And even you would have had already in the past the extremely correct idea, we wouldn't have noticed, because it would have brushed away by peer review or by ignorance, sheer ignorance, or too much information, and hence it could be printed in a book or printed in a doctor degree paper somewhere on a shelf, and we wouldn't even know. And the way of talking to each other in forums like TEGS and the ResearchGate as well, especially, brings people together in a way I had not imagined myself, and I made myself more public with the iSpace idea, for example, than I would have contact. I have my 10 friends around me, and my 10 friends are all doing peer review style work for me. So most people underestimate when I talk on ResearchGate something and I say, I'm sure. That does, of course, not mean that I am sure. That means I have talked to people way more clever, way more experienced in physics, and they have been sure and telling me that they are sure, so I am sure, because I trust them. So it would be too complicated to explain to anyone. So the short form is to say I'm sure, and then nobody believes you because it autodidact. What is he sure about? And does some multiplications. How can be that ever correct? Is too simple. But when you look it from the perspective of your physics friends, and you know that everything is connected to everything else, and you just found the peak of the iceberg, and see, I know how it looks below the water because my theory does this and this. Then all others can't see that below the iceberg until the Titanic hits. And what I'm absolutely sure is the scientific Titanic will hit soon. We will be alive, Rajan, when the Titanic hits. And all of physics will, as we know it by now, do a complete sink in the ocean of history. And it will start not with relativity, because it's still Einstein is on a holy podest level. And let's clarify from my point of view. For example, in this list, you mentioned Einstein. Why is actually more the important person of the next talks? But take that as an inspiration from my point of view. What Einstein was clearly correct with, what most people would, some say even that is bullshit, but let's get scientific and say what we do absolutely know for sure from experiments and his theories, which we can agree on and will not be established wrong. And I say the most important thing to start with is the speed of light in vacuum is constant. The speed is c, so when you have unit system associated with it, it's 299792458 meters per second, or in iSpace unit system, iSpace IQ with this golden ratio, iSpace meter over 6961 iSpace second. But whatever you define there to make it a value, that is not changing, and is not changing in integer theories like iSpace, able to derive the constants of nature, and is also not changing in Gerd's theories or other ones' theories to say space bends. So there seems to be a universal agreement on that light is really running on a constant speed when it is in vacuum, and nothing ever material with the definition of material, anything actually not light, whatever that is now, anything with a non-zero rest mass, to be precise, will not be able to ever reach this speed of light. And this is what all agree, but this is only one of the things. And you also rightly said Einstein got the Nobel Prize not for the theory of relativity, but for the photoelectric effect. And the photoelectric effect in its own, to add a comment to your very good introduction, is actually as simple as that. When you have coins and I give you the energy equivalent of 100 cent coins of euro money, and you have €1 in terms of euro money, and I give you a bag of 200 kilograms of cent pieces, and you build a cannon and shoot that cent pieces to some metal surface and measure if electrons come out of that, and with the image of the picture that coins would be light particles of a certain frequency hitting that metal surface. Experiments tell us that exactly nothing happens. So nothing would be in the sense you might even heat up by the thermoelectric energy you transfer by the heat. I mean, we all know from today, if you put a laser on a metal, you can melt it. This is just light what melts the metal here, but it's not light melting the metal, but the incremental photons energy up to a 0.2 dense per cubic meter that melts the metal's atom into a fluid form, where aggregated in a, well, one would say electromagnetic, but I would just rather say crystallized form of the metal, which makes the atom positions deterministic, while when it's fluid, it's not deterministic anymore. There's this randomness of Boltzmann also in. And with that simple thing, most don't understand, if I would have only thrown not millions of that cent coins, but one single €1 coin, I would have gotten immediately 1 electron out of the metal and could measure that. So when I throw 100 cents in 101 cent coins, it is energy equivalent to the euro. But obviously, because 100 cents is €1, but nothing happens with the metal. And once you throw €1 or €2 or €3, in quantized form, you get 1 electron, 2 electrons, or 3 electrons out of your metal into movement. Or the reverse, you put an electron in and get a light emission of that. And that is what Einstein got the Nobel for, proving that. Or not proving that, predicting that, and then who was the one who did the experimental proof on the photo effect? I would have to look, I forgot. But you can add that to the presentation probably, that you see this balance of an idea and someone in the lab really not much afterwards comes and proves that. And the normal understanding of intuition, where they say when I have thousands of €1 coins and shoot them at a metal, should be equivalent from an energy point of view to shooting the little bit heavier, bigger coins of €1, €2, €5 or something. Would it exist in a special edition? That is not at all clear why that should be that way. And this is where the quantum arena gets weird, where we have non-intuitive understanding anymore of why 100 cents is not the same as €1, while actually the energy amount of these is exactly identical. And this is where we are with this kind of interplay. And I think the quantization effects are underestimated. I have been working in very deep level in my spare time, when I have spare time, on the quantum of time recently. And maybe I'm able to make a dedicated session, an intro session, not just on iSpace as I did with the brilliant video in TEGS which we had with Emmanouil together, but really this is a 65 to 70 lines of Mathematica code. So think every line of Mathematica code would be a single equation. And every equation takes about a minute to explain and clearly show. And you have an hour of a presentation with an hour of discussion time afterwards, where we could see that step by step, nothing is wrong with what I'm telling you. And step by step, like checkmate in 64 steps, you have to either exit the meeting, said boring, I don't believe you, Christian, exit the text and said, this cannot ever be correct. This is completely free to like if you do a presentation in a larger audience and the professors of old school will stay up and leave the room and say, this is nonsense what he's telling. Yeah. But some of the younger ones maybe are just curious to falsify your what and stay there and follow you up to your arguments when they suddenly are checkmate after 64 steps without them knowing what happens to them. And I don't need to prove anything using that sequence because the sequence is self-explainable. Every of the steps is trivial, completely mathematically multiplicative, first order multiplicative trivial. No higher math, nothing. Anyone, even a 5-year-old child can understand that. And when you not after every of the lines, then after the about 64th equation is a hard proof that the electron mass in electron volt and kilogram in 2 different unit systems depends on a single physical entity of time, a human artifact induced by the SI system, which all our measurement values use, because otherwise they would not be compatible lab to lab. So even if you use CGS unit system, it's not so much different going from meter to centimeter. That per se doesn't hurt, but there are some implications with the 4 pi parameters in the epsilon 0, which are not funny at all. So I strictly stay in the SI unit system with iSpace SI, and I strictly stay in iSpace IQ. And after 64 of these steps, I have shown to the audience reproducibly and reliably. I really tried that with quite a lot of my people in my private background, and they were all stunned. I said, it can't be that easy. It was like, you just saw that it is, yes or no? So, and then the answer is yes, or they wouldn't have be asleep while talking. So if it is that simple, it should be able to convince the world that we have indeed a quantum of time. Now, when we have a quantum of time, what does that mean? And the interesting thing is into the philosophical area. What I can show you what that means. I don't want to grab beforehand, but that you see what the impact level of such a quantum of time is. It is not just another quantum effect which you have like, okay, added to the list of 1,000 quantum effects we had found from what all kinds of things have been done in the last 100 years with quantum mechanics. They're all cool in a way. Yeah, they're completely complicated experiments. They're like Thomas precession and stuff, you name it. Yeah, there's stuff there which we all know from the books. But a quantum of time does the following. When we have agreed in step 1, and would you say yes, agree to the speed of light is constant? I think yes, right?
Yes.
Okay. So when you agree,
constant the flat space or the vacuum.
Agreed. Just for the argument that light in vacuum is going with the speed of light c, and nothing ever will change that. No impulse, no power needed. It's just running forward until it hits some other atom. Yeah.
Yes.
So when the speed of light is constant in whatever unit system you define, and the speed is a meters per second operation in whatever unit system, and you define the second, just define it, not measured experimentally yet, but theory defines the second as an 1/6961 prime number. This is I-space second technically, but even if you don't know that, you can take the inverse as a frequency, and 6961 are an integer form of hertz, and you only have multiples of that hertz in whatever unit system that is transported. When you do that in SI unit system, you have to immediately agree 6961 is constant. This is an integer that does not bend. This is not 6968.9999575. This is 6961 or nothing else. Not one more, not one less. And hence is also constant. Now, in any simple triangle, volt, ampere, ohm, or whatever triangle you might have, you have an exactness on two of the parameters. You mathematically get an exact third parameter, right? You cannot have a little bit different parameter for the third if all three are dependent on each other. So when you have the speed of light, volt, which is meters per second constant, and you have the second constant, you now, if you want it or not, have the meter constant exact as well. You can define the meter in multiples of pi, or you can define the meter in whatever non-fractional units you name it. You write the number down. It can be an arbitrary long human artifact number, but it is exact with respect to the exactness of the time before, and the relation meters per second of c is exact. Now, when the meter is exact, and the second is exact, and the c is exact, and you know that the quantum of action from Planck is exact, which is widely accepted. I don't need to explain that. So we know that the quantum of action of Planck has eliminated the ultraviolet catastrophe, which you mentioned in your presentation very well, to become suddenly the black body radiation, where the curve does not exponentially go up, but goes up and comes down again, as it should be in the Ofen curve, which is all well known in the books for black body radiation. And the only thing, no, it's not really true, but de facto, the only thing what Planck has changed with respect to all of the predecessors which have tried differently, they get unphysical wrong results, because energy obviously in front of an oven is not infinite, or all the bakers would be dead a millisecond later. As the bakeries are still intact every morning, and the bakers and the sales personnel is not dead in front of an oven, obviously the energy is distributed in a different way. And with the knowledge of Planck, which is obvious to us, but at the time was not at all obvious, to quantize a value. So what does that mean? You give him not only a maximum value or a minimum value, that will be the Planck units. So the minimum time as Planck time, and the maximum energy or Planck energy or whatever. That is a consequence of all that simple Planck constant normalization. But what you give it a definite value, which is an integer in a sense, when you put it in the right unit system. You have 1 Ha or 2 Ha or 3 Ha, but not 1.75 Ha or anything like that in between. So that is what unit systems do. They do multiples of a single base value. And normally the single base value is a human artifact, in the sense of we define it to a meter. How long is a meter? They put your arms off and measure and say this is a meter. And it's irrelevant what you do as long as you define it thoroughly. And the kilogram, it's same. We take the kilogram as this weight, put it on a balance. And if the balance is horizontal, then we have on the left side, the right, the same. And we define if that is a kilogram, we can multiply the weights by multiplying them in exactly the same way and sending them out through the world, and just invented calibration, so that you always get the same amount of food when you buy something, or the same amount of material when you buy something. They were all historic, really deep inventions by simple things who were really not important for science. They were important for everybody, because when you buy a kilogram of oranges, it is different if you have one orange more or less, when you would just estimate how much is the precise weight of something. Now, for unit systems, that has an implication. When the Planck constant is exact, and we already agreed that the speed of light, meter per second, is exact, the quantum of time was assumed exact, and hence, as consequence, the meter was exact, and the action is exact. Force is defined as volt ampere second over meter. This is volt ampere is obviously the watt, from James Watt. And when you have a watt times a time, you have to pay for your electricity bill. So you have volt ampere times second is joule. This is the energy definition. And when you divide that over the second, then you have a force. Volt ampere second, second, sorry, when you divide it over the meter, volt ampere second over a length, then you have the force in Newton. And with such a volt exact, an ampere exact, and a second exact, and the meter exact, you would have a quantized force. Now, I have not yet shown in my argumentation chain why the volt and the ampere should be exact. Now, the ampere is exact, and it's easy to see because the ampere is charge, and charges move by 1 electron or 2 electrons or 3 electrons. So if that is done now in quantized units like golden ratio I-space ampere, like in the I-space IQ unit system, or you define a human unit to that, like Coulomb, and that is exactly the number of the inverse of the electrons measurement. Coulomb charge is just a numerical trick. It doesn't change anything on the physical argument that charge is transported in multiples of electrons units, and hence is a physical multiple of an integer. Now, when the ampere is a physical multiple of an integer, the second is a physical multiple of an integer, and the meter is a physical multiple of an integer, I just need to show you that the volt is also quantized and not arbitrary, right? And now we have the quantum Hall effect. The quantum Hall effect is h over e squared in ohm. Ohm is nothing else than volt over ampere. And the quantum Hall effect jumps in steps, of a theoretically linear curve when you put a magnetic field of about 6 to 7 Tesla in a, it's hard to do, but the typical labs power magnet, I don't even need to think it's superconductive. You just need a very big magnet and the power electricity to do that. So you have your typically silicon chip measuring the quantum Hall effect there, exactly as was done, which led us to the detection of the quantization of the ohm, literally. And you cannot quantize the ohm without having understood that the volt needs to be quantized, where we said when the ohm is quantized, in the quantized levels only physically, not in the levels in between. Then at the quantized levels, for sure, we have ampere as 1 electron is quantized, we have the ohm quantized, hence I can prove on the horizontal levels of the quantum Hall effect, the volt is quantized, whatever you think. And the I-space theory has shown that the equation for the quantum Hall effect is as simple as 2 times 3 times 6961 volt over golden ratio ampere gives the SI value and the I-space SI value of the quantum Hall effect. And hence, if you look at it from a historic perspective, of the last 5 minutes I talked, I showed you that volt is quantized, ampere is quantized, second is quantized, meter is quantized, and the speed of light is quantized. Now that means the force formula, volt ampere second per meter, in the minimum quantized integer stuff to be multiplied up by n, is also force quantized. Now, when the force is quantized, the action is quantized, the time is quantized, the electrical ampere, the electrical volt is quantized, and you construct the kilogram by Einstein's simple equation. Mass is speed of light squared, energy is speed of light squared times mass. You take the electron mass, which is quantized because it's multiple of the electron, and have the speed of c squared, which is quantized. So we already know on the left side the energy must be quantized because everything on the right side was quantized. Now, when you divide the energy by c squared, you get the following equation. You get volt ampere second, which was energy, the joule, divided by c squared, which is meter per second. And when I write that out and simplify, you get volt ampere second to the power of 3 over square meters. And that is kilogram. And now we know the kilogram is not a human artifact anymore because everything we put into that simple unit kilogram, if you do it in I-space IQ units, is quantized. Now we have the multiple of a mass quantized. Now wait a moment, what stays? We have volt quantized, ampere quantized, meter quantized, second quantized, kilogram quantized, Coulomb quantized. Oh, wait a moment, everything is quantized? There is nothing you can argue against anymore. Everything is quantized in such a unit system. And only because of a single unit is quantized for sure, and that was the time. So what scientific revolution of 2022 and on is waiting for is an experimental confirmation that quantum of time is real. And what would it need to get an experimental confirmation for a real quantum of time? And the answer is, we have people here like Professor Hensch in Munich, which invented something he got a Nobel for about 10 years ago, and that is the frequency comb. And the frequency comb is taking one input ray of light into a so-called comb. Actually, think of a super prisma. And that comb splits up to about 1,000 individual, precisely segregated, precisely distanced, equal distanced single frequencies of light with a different color. So you get a color comb, but you know, and you can count each peak in the color comb directly and associating a specific mathematical frequency, because it's not like a prisma where you get a continuum of colors. It is a comb where you have a discontinuum of colors and you can count them. And counting means you shift your experimental precision board by some screw in the nanometer range until the positive and negative interferences of the comb pins give you the maxima, and hence you can count maxima after maxima after maxima, which is a tedious work. And that allowed, and was basically the way he got the Nobel Prize for, to increase the time precision of electronic devices in the gigahertz range, which are already in 10 to the power of 12. Yeah. No, sorry, not gigahertz. Gigahertz is 10 to the power of 9.
10 to the 9.
Yeah. So the experimental precision in certain electrostate devices were 10 to the power of 12. And that was the maximum the clocks could do. So the frequency counters could not go better than 10 to the power of 12. And with the invention of the frequency combs, they could go 1,000 times more precise suddenly. And they could increase, and this is a leapfrog jump from 10 to the power of 12 to 13, 14, 15. Recently, it happened, the frequencies got from 15 to the 16, 17s, 18s. This is attosecond range. You probably heard about attosecond physics, where you have a high-end flashing resolution in the attoseconds and suddenly see such a kind of steady-state electron in the orbit, and you catch it while it is in a specific position, orbiting left, right, and you really see the bulge of the electron where it is relative to the atom in a photo.
Somebody got Nobel Prize recently.
Somebody got a Nobel Prize for that as well. But what happened technically before that happened? So very clever people in the lab said, when we can have a frequency comb, what would happen if we take a single frequency of the comb, not near the center, but more on the right side of the comb, not directly on the exit side of, but so in 2/3 of the comb where the signal is most clear still, and put a frequency comb behind the frequency comb. We would take that single frequency and put it through a second frequency comb. And as a frequency comb will increase your precision by roughly about a factor of 1,000, giving you an experimental precision of, say, 400, 500 times really effective lab measurement-wise, including all error corrections and the unavoidable measurement errors you have there. You have a times 500 squared factor of increase of actual precision and a theoretical maximum limit precision of 1,000,000 times more precise than 10 to the power of 12. Now, this is exactly where we are at the moment, and the current atomic clocks and the new atomic clocks to come are designed in this kind of range, leaving the current definition of the Braunschweig atomic clock from the cesium atom, which is way lower in frequency. It has a higher stabilization and all that by the worldwide coordination of multiple clocks worldwide. But the single precision of a single atomic clock of this new type is about a factor 1,000 times precise than the current cesium clock. And all I'm saying is, when will a doctor degree work come to the place, maybe in Garching even, where some physicist has the crazy idea to say, what happens when we put 3 combs in sequence? Now, when you put, again, with the same trick, taking the so you have to understand that the picture I have seen of the lab with the 2 frequency combs is 20 meter in size length and 10 meter wide with full of lasers, optics and stuff. This is horrifying of already of complexity, yeah? Now think of a lab of the size of, say, a football field. I don't know what it takes, I just assumed, yeah? And put even more devices, lenses, lasers in, and someone would manage to get a 3rd comb in that sequence. What would happen? Purely mathematically, we would increase from 10 to the power of 18 to 18, 19, 20, 21, right? So again, 1,000 times more would give us the peak range of 10 to the power of 21. And it happens to be that the ice-based spacetime is about 1.0010 to the power of 20 hertz, which inverse of which is about 1 to 10 to the power of minus 21 second, exactly in the range of such a frequency comp. Now, when you do the experiment right, you would get another Nobel for even more precise, or it would be boring because, yeah, what is the difference between 2 or 3, and you do not get a Nobel? This is not the thing about. No. The interesting thing about this, the ice-based theory makes a hard prediction and says there is no higher light emission frequency than induced by ice-based spacetime. And in nowhere of current physics, neither relativity nor quantum mechanics, this is predicted. They think they can increase the frequencies ever higher up to Planck frequency, and light will always be emitted. And I tell you, that is shit wrong. Because the electron is a ring particle. It is a side of it that in ice space is a 10-dimensional thing, a 6-dimensional. Forget the dimensionality. If it is a torus, and many in string theory and otherwise think so, then if you magnetize a torus in a certain way, that the electron has a positive and a negative end, and not be just like a normal monopole which you work with, but a normal dipole magnet. And you do the ring right, you can buy such ring magnets in internet to make loudspeakers, namely. They are very effective, and if they are not polarized within the ring of left and right, but as two areas in top of the ring, then something crazy happens, namely that the magnetic pole of the North Pole is inside the ring from the top, and the magnetic pole of the south of the same ring is on the magnetic center of the same position from the bottom. And now something physically happens which the magnet doesn't like. The North Pole and the South Pole of the ring magnet, a static, non-moved ring magnet, cannot ever be in the same place. This is physically forbidden. So what happens is, and this is my picture of idea how an electron actually works and where the ice-based spacetime comes from. The electron is a what is the word for transmission frequency? It's like a transmission line with one element with a self-referential frequency of that of the electron, and the electron's frequency is exclusively determined by electron geometry as envisioned by the paper of Emmanouil and me. It's exactly that horn tube thing which is in Emmanouil's paper, with the south on top and the north on the bottom. But if you would construct a magnet precisely in three-dimensional thing, it's more precise. I mean, a real magnet has multiple atoms, yeah? So it's a macroscopic object. But when you think the electron is not a macroscopic object, but is just existing of that field, then the same logic pushing the ring magnet's north-south pole constantly forth and back with a certain macroscopic frequency would go to the ice-based spacetime in the true electron ring magnetic thing. And that is a maximum frequency the electron can emit, because the multiplicative equation of ice-based tells you ice-based spacetime. So 1/6961 ice-based second times golden ratio ampere gives you the Coulomb force. This is 1 Coulomb per definition. And if you do that in SI units, you have this ice-based spacetime, which is 10 to the power of 21 minus 21 seconds about, times golden ratio ampere. So the golden ratio ampere is the same golden ratio ampere as in ice-based units. And that means it's a quantum. And the quantum of time is also there, but the human artifact prevents that you see that. So SI has arbitrarily defined the time. And when you push the human part of that time out, the quantum time stays and remains. And hence what you will see in a frequency comp, when the idea which I see, I can literally see that when the experiment would come, is that the remaining part of the frequency comp, where they expect 1,000 spikes as well, will break down after, say, 250, 300, 400, depending when they cross that ice-based spacetime border. The electron will refuse to emit light after that frequency. And that will be the experimental proof of ice-based theory. And then the world will break down, and completely, because if one part of ice-based theory is correct, necessarily by logic, the rest is also correct. It's just integer multiplication. And then it's game over for a lot of theories, including not all, but a large part of quantum mechanics. So all of quantum mechanics on the size smaller than 10 to the power of minus 13 meters, which is not exactly 10 to the power of minus 13, of course, as an integer value, but technically the root of the Bohr radius times the classical electron radius. So if you measure that value, or if you take a theoretical calculation, doesn't matter. But exactly at that end, the geometry changes from that what we perceive as a continuum. Einstein continuum is also not continuous, but that is a different thing altogether due to the proof which I just showed you. If everything is integer, Einstein continuum has very, very little pixels, but nevertheless, it's also not a continuum. You can assume it as a continuum mathematically, but what you do actually is summation and not integration. If there is no continuum, then integration is your approximation, and the summation is the correct thing and not vice versa. And that breaks all of physics books, including all of quantum mechanics books, just purely from a mathematical part. And quantum mechanics gets invalidated to not be usable anymore below 10 to the power of minus 30 meters. And from there, I-space rules with pi equal 3, with the hexagons and all that, what I-space geometry predicts. But to see that, we need a clock which is in the domain range of 10 to the power of minus 21 seconds or higher, and higher is not possible, and this is the prediction. Here you see, this is such a simple idea, but that simple idea is in the domain range of the simple idea. Simple is not simple what Max Planck had. Let's quantize the momentum and see what happens. And if you quantize the momentum, a completely wrong ultraviolet catastrophe producing idea suddenly gets completely correct equation without any further change. Purely mathematically, suddenly the correct temperature curve for the black body radiation is there. And this is what I predict for all of physics. Once you apply the feature of quantum of time, so when you quantize everything, suddenly everything is correct.
Is it like chronon? Is it a limit? Is it like a chronon or something like
yes,
that?
You can think it of as a chronon, I think, yes. The quantum of time is a minimum amount of time you cannot physically get below, and that's it. You can have theories which are continuum assuming to go below that, but they're all wrong, because normally it's assumed Planck time is that time. But Planck time is 10 to the power of minus 44 seconds, and that is 20 order of magnitudes away from the physical reality, and nobody expects this. Nobody will see that coming. They come out of nowhere. The experiment will be there, all will be shocked and say, what is going on? Why is our physics breaking down after 10 to the power of minus 21 seconds? Then they all do an internet research and find that Christian Wolff predicted a quantum of time. I said, oops, how can that be? And it can be because it's that simple. There is nothing you need to understand. It's just multiplicative physics. And if you start with one integer thing, have a triangle, you get the third integer, if you want or not. This is consequential logic, and that's cool because it's so simple.
Yeah, I don't know whether you had a chance. I work with Emory Taylor, and we have developed something called discontinuum physics. What you're talking about is similar. It actually falsifies everything, kind of. I don't go that far, but yes, also we work together because I do the mathematics. Essentially, his fundamental argument. His argument is, fault-free. He's perfect, like a lawyer or perfect logic he has. But I develop mathematics for things. So, and then we are like 10 papers almost. And they're one by one very carefully falsified most of the relativity, Einstein's continuum theory, how Einstein himself falsified that. Then also the quantum mechanics that you talk about, we said that again, it breaks down. So we call it discontinuum energy field, and it's very similar to what you're talking about. And I believe, and I work separately about the matter and how the supernumera thing becomes a particle. And the quantum comes because the time does not have any meaning in the supernumera level. So the sublunary level, you have to have a particle. As long as when your particle is quantized already, a particle is a quantum.
By definition.
By definition. So the time then has to be quantized from that point of view. So it kind of indirectly verifies your thing that it has to be from that argument. The time there has to be a particle which creates events that creates time. So if there is no particle, there is no time. So the particle by definition is quantum. So the time has to be quantized.
This is an interesting question. If there would be no time, if nothing would tick. I haven't thought about on that detail level yet, but I think it goes in the right direction at least, because the electron is its own clock. So in another word, every particle is its own reference clock.
Yeah, exactly. That's what I'm developing. A clock, because I develop now, there's I have one paper which talks about the tensor of time. You know, the time is about vector and scalar. And I have developed I have already published up to 4 rank 4 tensor. Now, really, when you talk about group theory and everything, it has to be a rank 6 tensor. So that's the next paper I have. Some material I have, and then I have put them together, and I have proved, like you mentioned about the action, that time actually, let's say it's tau alpha beta beta. That's the vector time. Is the second order of the action. This action is s. So del square s over del x mu, things like that. So it's a differential of the action. If there's no action, there's no time. If there's no event, there's no time. So time is directly connected with action. So it's more than our entropy. I mean, entropy may be an action, but I think the vector aspects of time comes from the action. So if you develop, if you know the action, we can find that time, and that's a vector time. And there are scalar time also. I'm developing that based on the group theory, things like that. How it will have 6 vector components and 2 scalar components. And the clock, now I have developed, I'm just ahead of my time and just putting it, because YouTube is kind of copyright. And, you know, when I write that, I think I can still use that copyright. I have talked about it. Something called time loop. So we have something called, I'll talk later, but it's like an umbrella. You know, graphically, you can think of an umbrella, an open umbrella, and that has all these vectors coming in, the 8 tensor, develop that. And then you have equivalent symmetric upside down umbrella and top. The top umbrella eventually becomes like a dome, and the bottom umbrella becomes a chandelier. They put them together, get space. But they can collapse. They can collapse, and that umbrella, you know, it's a folded umbrella that shows a certain clock, a scalar clock. So you have 2 clocks. What Einstein talked about, proper time, real time, but actually I just call it local time and the global time. So one of them is pointing to the local time, the other one is pointing to the global time. Let's say you have a clock in your Munich. There's a clock, or Ben, Uncle Ben. That's kind of, that's not really a global time. The actual global time is the local time, like on Earth, another one on, say, a black hole, a supermassive black hole. So right now it's pointing that, and what is connecting them is a Euler angle. Euler angle kind of thing connects them. So they are at, you know, they are not collinear. They are as a torsional angle. So they'll be higher dimensional, like four-dimensional thing that's connecting. So the umbrella is pointing like that. And I developed something called time loop. What happens is that, for example, Halley's comet could be the one that can disturb that. So whatever you do, it resets to that. See, you may do a lot of things locally, but eventually still in a particular time loop, it resets to that. So one clock in the folded collapsed level will point to a local time. Like I in my clock, let's say it is 11, 18 or whatever. In your clock, it may be different. So it is pointing to that. And another clock is pointing to, say, supermassive black hole. But it need not be exactly that. It can change. So like comets and things like that can vibrate that when it's in the umbrella form. And now, you know, when it goes to the next time loop, it will point to a different, you know, different things. What happens is that whatever you do resets to that. See, that's what I was measuring from my young boyhood days, that you do whatever you want, you know, operations, but it resets to 1960s, for example, a lot of times, whatever you do. And that our global events, we relate to that. Okay, you talk about all the developments, but again, you know, the TV and other things, they talk about politics and everything. We again regress back to 1960s. That's what we have, the Cold War and everything again repeating. Same thing that Russia, the US, everybody is doing is very similar to what happened in the 1960s. So no matter what, the clock is resetting itself and it again go back to the thing. So that's called a time loop. So 1960 to 2040. It's about 80 years. I found independently, it's about 80 years. It could change depending on the thing. Next time it will be slightly different. But it's very close to Halley's Comet, which comes every 76 years or something. That's very precise thing that's happening. The Halley's Comet comes at almost precisely in that time range. So, and when that next Halley's Comet, I don't know when it's going to come, it will vibrate that and it will change. The next reset will be at 2040. So like you said, that time the physics could all be changing or totally revamped. And 2040, and then the other clock, in the collapsed umbrella level, may point to another black hole or something else, and the Euler angle. So which means that there is a local complexity and the global order. The global order then becomes global disorder and things like that, and the complexity physics aspect. The order is more like chemistry aspects, and I have plotted this one. So the time loop is determined that, and we actually change a little bit with global warming, other things we do. We introduce the disorder. So actually, what I find that the time loop actually should have gone like that, nicely gone down. Instead, showed a dip because we did something locally that we should not have done. Maybe global warming, something else. Even our thinking, everything matters. How people accept that. A lot of times, like you have described very nicely, logically, everything, right? You are proving every step of your way completely, but people are not like that. They said, okay, this is the way it is. You have to accept that, whether I'm right or wrong. So they are bureaucratic, they have power. They will say, okay, just assume that, just use that. But once you are proving, I know that I'm very impressed by your thing, because you are ensuring that you are proving it every step. And I also doing that as much as possible with mathematics and things like that, every step. Because I question myself, I kind of go through something called hardballing. So I go to hardballing and say, okay, I'm thinking that way, I may be wrong. So again, I go back and then, and that's how I come across yours. So I don't accept anybody, just the face value, even your thing. But when I look back, a lot of things are confirming what you're saying. I say, okay, Christian, somebody else is saying Christian is wrong, things like that. But I go back and then check that, okay, it comes to the same thing, but I'm coming from a different angle, but it conforms to what you are saying also. So you are a very logical thinker. That helps a lot, in your computer, everything. But I am more from physics.
I'm not claiming that in any way I would be able to mathematically understand on your level string theory or things I have seen in your presentations of multiple times from the years of we have now these sessions on. I'm coming from IT, and what I can solidly state is I am an expert of integer. Boy, I'm the expert of integer. So this is what most physicists lack, because the physicist standard education is mathematical in the sense of a continuum mathematics with a complex numbers, with a class R, where everything is subdividable an arbitrary number of times, in other words, continuum. Mm-hmm. And they are trained their whole life with that. And only later, when they have to, with all due respect, program a little bit Fortran, they enter my range and have discrete variables in Fortran, even if they call it floating point values. But floating point values, when you look deeper, are integer values, integer exponents, and an integer sign, which are combined to something you call a floating point number. But when you look inside the computer, there will never be a floating point number. They are three integers, and combined by a logical entity, like a basket of three integers, you call a float. And these integer values also have overruns and error messages, like division by zero error, like none, not a number, overflow, underflow, lack of precision. So different bits in the electronics of a typical ALU, of a arithmetic unit processing for floating point numbers, integer numbers, and all that are just an acceleration way inside a modern CPU. But the operations, if you do it with a Turing machine, so the simplest machine you can have is a Turing machine. It's a single band of instructions. And in a hypothetical very, very long-running thing. That Turing machine is proven to be computable for everything we do in normal computers. So for Neumann computer is mathematically proven to be Turing compatible, which means a simple Turing logic engine, when you let it run long enough, will be able to do everything we do in assembly language or in C or in whatever higher language. So including all its defined data types. So all these data types, which we in mathematics given for granted, are actually informatical data types. Whereas the true mathematical ones are only in your brain. They never have been inside a computer. You can write that, what Newton is doing. Newton not invented that, but sort of what the first formalized mathematical trickery, I call it trickery if you allow me that for a second, of continuum mathematics to show the soft, smooth motion of the planets without friction, okay? And when you look deep, you would need in a computer to visualize that, a grid, because to visualize it on a screen, and if you don't have an analog oscilloscope, which we also could think of very, very, very long time ago, you have pixels on your screen, and that pixels are part of that grid. You would calculate it with required precision. So when you look on a computer, you already lost it to me, and I win, because inside the computer, nothing of your completely analog assumed universe is remaining. If you play with voltages with an analog computer, with operational amplifiers, condensators, capacitors, and all that kind of things, then I agree to some extent there is still physics in place, which I could argue with you, yes, that is some continuous voltage, and I cannot prove 100% it's discrete, because the steps are too small in the universe to see that, because as I told you, the steps are directly imposed by the high-space basetime, and this is 10 to the power of minus 21 seconds with a unit volt, which is golden ratio ampere, and 1 unit volt, and that is too small to measure yet in the lab, of course. Yeah? So from your point of view, is even rightly a continuum. Now, Einstein has...
Gerd, for example, is mentioning that, right? Gerd
absolutely. So there is one interesting, not just anecdote I want to explain. So I was at Gerd's place a couple of over half a year ago, actually, in Augsburg. And I came with the attitude, from my point of view, arrogant attitude, to show that everything he was doing in four-dimensional spacetime with continuum is completely wrong. And I wanted to do that, that was my plan, by replacing his floating point numbers with 9 to 10 digit measurement precision with absolute geometry of I-space, which is infinite precision, and mathematical logic of golden ratio, P, P3, you name it, you know that stuff. And I failed miserably in front of Gerd's eyes camera, to put it that way, because what I actually proved is that our two models are compatible. I put that stuff in his analog equations, which assume four-dimensional continuum. In other words, integration equations, differential equations, which mean integration and differentiation is in place with a full virtual in your brain only assumed continuum. Put my geometry in, and literally half an hour later, while he was cooking in kitchen, I was preparing the presentation why he is wrong, and derived with his equation an equation which I could not derive by I-space myself, but his model could, and it was the proton mass. And if any proton mass would have come out, I would have made a division of proton to electron mass, Googled the current value of proton to electron mass ratio, and showed him that is outside the measurement range, eat and drink something together and drive home, and would be happy that I was right. But I was completely wrong, because the proton mass coming out with his model was exactly fitting the Mathematica 7 values, which I am the reference values I compare I-space theory to, up to the 9th or 10th digit after the comma, which is completely impossible by the chance of 1 to 10,000. And I mean completely. And when we analyze
it doesn't falsify your I-space, right?
Not at all. It shows that everything, some magic mechanics in the continuum has integer multiples of I-space base values, making it fully compatible.
Ah, that's great. Yeah, I would think so. I would think that I agree with you about the quantization. And one of the, I used to work with a professor of physics. He's a quantum physicist. He's no more. He's the one I talked, because I worked in material science and mostly experimental things like scanning internally, microscope, things like that. When I came here to Arizona from Pennsylvania State University. So when I worked here, it was a Department of Defense project. So then he was here. He was a professor of physics, quantum physics, and we used to have meeting every Saturday. He used to take me to a restaurant, and he's real professor of quantum mechanics because he has come to Europe, different places. He has stayed there, and so he asked me. So we are, because at that time I am looking quantum mechanics from the point of view of material science and quantum tunneling, things like that, which I use for electrochemistry also, for the hydrogen proton tunneling type of thing. So I was talking about more from the experimental observation and more from that point of view. Then he asked me, he's a theoretical physicist, of course, quantum physicist. He asked me, is a time quantized, after the thing. So this is the last talk I had with him. And that was the thing that kept me, it actually made me more theoretical physics, go into more the theoretical because of him. Discussions over a year or something, more than a year, almost every weekend. And so I got a fundamental tutoring from him about a lot of the quantum mechanics, and he clarified a lot of doubts I had. But he asked me about time quantization, and at that time I didn't answer. I think it was good of me not to answer it because I had to think a lot more, analyze a lot more before I can find out. And then from what I came up with the particles and what I described, and that time has to be quantized, and you are actually independently in a way proving that time has to be quantized. So that's fantastic thing, because I believe deeply that anything in sublunar space had to be quantized. Now I have come up with yes, absolutely. So yes, so the following thing I have come up with. The problem is the statistical and probabilistic aspects. So what is statistical? What is probabilistic? I think the following. I have to check the conjectures. The sense, I call the sense, which probably exists even at the superlunar level, has to be statistical. Whereas both the space and time are both statistical and probabilistic, which means they're stochastic. And what it means is that when you talk about, that's why it's a complex. Is a stochastic continuum or stochastic quantized, quantum. And that's why we have to prove separately. If the time is quantized, then eventually you can say the stochastics has to be quantized. Only from that point of view. Stochastic by themselves can be both continuum or discrete, or both, or a combination of the both. But if we can prove separately a time is quantized, then you can prove that the stochastic has to be quantized, which means that events are quantized. We don't see that, like you mentioned, the jumps, electron jumps, things like that.
Rajan, if you may allow me to point you to a paper of myself, you might have not had the inclination or time to read that. Okay. And it's called about the simple relation of the Planck's H bar over 2 constant, which is nothing else than Heisenberg's uncertainty relation base value. And Heisenberg had initially very, very simple I-space-like integer matrix numbers used on his 2 weeks where he got sick to cure himself out on Helgoland in this little environment there. There's also a good paper on what Heisenberg actually thought when he did these calculations, which are historically well archived, but really understood by no one, not even the top of the notch experts knew what Heisenberg actually thought. I have a doctor degree work paper of about 70 pages. I've read it 10 times, I can still not understand it, but it is showing the steps of Heisenberg, which finally migrated worldwide into what became the Schrödinger equation, because everybody was thinking waves and Schrödinger gave them standing waves in a circle, more or less. Yeah. And I said, look, we can do waves, and everybody trashed Heisenberg's concept of doing equivalence. So there's a mathematical proof, which actually done by Schrödinger, that the wave equation of Schrödinger is mathematically equivalent to that what Heisenberg did with the matrices.
Can you send me the paper? I appreciate.
Yeah, I can send you. If I have to find it, that it's not on this machine. It's on somewhere.
It's not German, right?
I have it on. But if you give me time, I'll send it to you in the background.
Sure.
Yeah.
Thank you.
The other one, which I'm mentioning, this is directly on ResearchGate, and that comes back to the last point you said before I interrupted you, and I had to interrupt you not to lose the thought on that, because that is extremely important.
Problem.
You said that the probability, which can be a multiple of integers or a multiple of a continuous random value, or a mix of both, shows the randomness in quantum mechanics in a way which is not explainable at the moment, because we don't know what kind of randomness goes into there.
Yes.
And I can show you that I have an equation based on I-space mathematics, where on the left side is assumed the Heisenberg uncertainty relation, like in a very general form, not specifically with say length and impulse or something. It can be multiple values on the left side. So it's left a relation. And when you multiply this left relation with the speed of light c in your given unit system, and I do that in 2 unit systems as usual, I-space SI and I-space IQ, to see the complete mathematical difference coming out. And you have that on the left side. So you multiply delta x mal delta e. So in German, Ort und Impuls, or location and impulse. Yeah? As a delta is always smaller than this Haar-bar half, which is the relation of Heisenberg. And on the right side, I have an equation that blows your socks off. The right side shows that is golden ratio kilogram times golden ratio meter.
Wow.
Yeah, now you got it. If you hadn't said wow, you wouldn't have got it, okay? So, of course, there's a term on the left side which removes the SI human time artifact properly from the physics. But the logic behind my equation is the following. The delta x is the most small thing, can be delta of something quantum, and the delta t is the most small time of something quantum. But the trick you need to see is you have to multiply that with c. Why? When you multiply it with c, you get an equation of kilogram times meter on both sides. So your hard to grasp action. No one really, even the top physicists, really understand what is the quantum of action. Everyone is saying action, but from an exponent point of view, this is volt ampere second squared. This is the unit of Planck so everybody knows what a volt ampere second is as energy, but when you multiply with another second, you can have a lot of things. You can have just like your electric counter in your house is running, and the longer the seconds run, the more you have to pay for your electricity. That is the trivial interpretation of volt ampere second squared. But the quantum of action is of a completely different caliber, because it also has the unit volt ampere second squared. And there are long debates going on in history of physics why the hell that is. So what is that quantum of action's unit? And in I-space theory, can you immediately see that? But when you define the quantum of action with a unit name, then you hide all these facts behind a human name like volt ampere, coulomb, and action. They always say the action, yeah, but they don't actually see what that means. And when you split the action off to volt ampere second and meter units, and do that in I-space IQ, and remove the I-space SI time section, you have on the right side golden ratio kilogram times golden ratio meter. It's sheer unbelievable. On the left side, you have golden ratio meter times that what is in the Planck units, namely Planck mass times Planck time. And that is physics. I cannot falsify that values. Planck mass and Planck time are the ultimate physics. And all that stems from the Haar-bar over 2 Heisenberg uncertainty relation. Now, when you assume that relation is correct, then you have a geometric value for the input values of that relation, because you can replace the right side with either the Haar-bar half or with the golden ratio squared. Is equivalent. This is an equal sign in Mathematica. So I'm not doing anything mathematically wrong. There's not an approximation. It's exact. And that changes everything. And that is a very, very complicated to read paper, because actually it is technically something like an attachment to a paper I have yet to write. And I had no time to do so. I haven't even written the peer-reviewed paper for the quantum of time yet, but I'm working on it. So that is, first of all, that simple paper on the quantum of time, which I push on every discussion in ResearchGate and shove it down the throat of the people. Oh, is this impossible? I said, okay, if it's impossible, do me the favor, read it and tell me tomorrow that it's still impossible after you have really read it. And most of the people at the time are actually shocked. Yeah, they're shocked. And I can tell you, if you allow me that, what people who have really read my stuff in iSpace talk now about iSpace after these years since we presented the text was nearly in January in 2026, already a year ago, and not a lot of people. I mean, this is very respectable. About 160 people have seen my video. That is really cool. So it is in the most areas of what your videos and Emmanuel's videos have also been, for the relative short range of marketing reachability we have on YouTube. So we're not going viral. Yeah. So, but no, that is already respectable, in my opinion, at least.
Yeah.
And a person has written me something. I wanted to state that to you if you give me the time to conclude. I just need to take my iPhone for that, and I read it off my iPhone screen.
Sure. Go ahead.
It is very impressive. It's the most impressive short text about 2 minutes, which I have heard about iSpace from an independent person. I have not talked to this person to write that to me. I have not in any way put the words in his mouth and said he should talk to that. So he's a string theoretical expert. He's writing a 150 paper long page, which is in the peer review of all these domains you would better understand than me from a string theoretical point of view. And he is always struggling with the dimensionality of the 10 dimension, as everyone in string theory is doing. That what are the free parameters there? What is concrete? And he said iSpace nails nearly all of his parameters to something useful, because I don't allow the geometry to deviate from golden ratio ampere. I don't allow the quantum of time to go off. So there are space constraints which just multiplied up by integers, which makes it completely clear for him, at least, for the first time, that he can now see how that string theoretical geometric approach to replace relativity in the near future might actually work out. And the text which I have been given was impressive, and I really want to give the readers and you the time. I pasted that to my friend Harald, which was also at the part when we did the text meeting, and he also said that is really, really impressive. And it says, goes like that: Dear Christian G. Wolf, I hope all is well with you. Firstly, I must apologize for the delay in my response. So he had needed 3 months to reply to a post which I made on his paper about iSpace and suggested he should have a look. But that was all I was doing, basically, because I think his ideas about 7-dimensional subspace time and these are quite related to what I do in iSpace for pure logical reasons, for more mathematical than any physical reason, actually. And he said, immersing myself into your work on the iSpace theory has been quite the enlightening journey, and I wanted to ensure it received the thoughtful consideration it deserves. Your approach is recalibrating fundamental constants through a geometric lens has genuinely captured my interest. The manner in which you've addressed the speed of light and Planck time using the iSpace IQ system presents a refreshing perspective on time's quantization, suggesting a unified geometric framework that could seamlessly bridge existing gaps in our understanding. Additionally, your straightforward yet profound derivation of the gravitational constant g within the iSpace framework necessitates a reconsideration of our understanding of gravitational interactions and the structure of space-time. This type of innovative thinking is precisely what drives our field forward. I was particularly captivated by your reinterpretation of Doppler effects within relativistic contexts. The analogy we think between Mach cone and the relativistic light cone as fundamentally representing the same phenomenon, albeit in different realms of physics, one with sound and one with light, resonates deeply within me. Your insights add a significant layer to our collective comprehension of these phenomena. The U-factor analysis. So the U-factor is another paper I made for Francois Zinserling. He asked me to calculate the U-factor, which is in turn a relativistic constant inside some theories of relativity. I was actually not aware what he's doing. I was just calculating that and see if I could do that, and made a full paper within 8 hours. It took me, I had not more time, so it worked. So he read also not just a single of my paper, he read more than one of these papers I have on ResearchGate. And one was the U-factor analysis, as requested by Francois Zinserling, has demonstrated the iSpace model utility and adaptability in advancing theoretical physics research. Such tools not only aid in the vetting of new theories, but also hastens the pace of theoretical explorations. This is what I always try to communicate to you and people critical on your end here in TEGS, that even if you don't think iSpace theory is the proper way to go, the tool of iSpace could be the proper way to advance your own theories understanding, because you suddenly get a magnification glass looking into your own values by exact values, not just by measurement numbers, which you can comprehend geometrically. So he said, the potential on the iSpace theory to weave together various domains of physics is particularly thrilling. Yet the path to empirical validation remains a critical step ahead. Engaging with experimental physicists to test these theories will be crucial in affirming the iSpace theory's rightful place within the annals of scientific achievement. And I can only agree. And this is what I told you with what I predict when you do 3 frequency comms, you might see that, or any other experiment which we'll do. The implication of your work for educational purposes are profound. The clarity and elegance with which it elucidates complex concepts offer a significant opportunity to make fundamental physics more accessible to a wider audience. Looking ahead, I'm keen to investigate how iSpace theory might illuminate some of the most persistent questions in physics, such as the nature of dark matter, dark energy, and the quest for a unified theory. I'm particularly interested in exploring quantum applications related to gravitational effects, an area where I believe your work could yield substantial insights. Your pioneering approach to these long-standing questions is not only invigorating, but also serves a beacon for the promising yet unexplored frontiers that await us in physics. I eagerly look forward to diving deeper into your research and contemplating how we might incorporate some of these groundbreaking ideas into forthcoming projects. All the best to you, Alessandro. That is Alessandro, which I will send you the paper, and so that you have a reference also to have a look on his work, which I believe has something to say. This is really groundbreaking also. And should it be peer review, we should invite him and have a text presentation as well, by the way.
Okay.
That will be on the level of complexity of that, what we have seen from others like Gerd and Emmanouil and so on. He made a PS afterwards even. PS, your endeavor to bridge quantum mechanics with general relativity through a unified mathematical language is not just ambitious, but could be revolutionary for physics. The dimensional analysis you've applied, so in using volt-ampere meter second and not the usual units, actually, is a testament for the potential for uncovering hidden correlations among fundamental constants, suggesting a universe more interconnected than we've previously imagined. This is exactly what I tell you. The values of G are not accidental. The values of G are not varying. So this is where Gerd's theory would deviate from mine, where it said G must be deviate, but both is correct. This is the trick. Both is correct. It deviates and not deviates at the same time, cannot be, but when you need relativity and relativity is wrong and needs a compensational factor, it deviates until you multiply that deviational factor, in which it would always give 1, and then it not deviates anymore, and then you end up at iSpace theory. So both is correct. And I now understand by a paper of Lev Verkovsky, which is a Russian scientist who made 20 years ago published a paper in Russian, who was really not noticed because published in Russian and not widely known, who said the theory of relativity is wrong from the beginning. Not the theory is wrong, so the theory is completely correct in the sense of measurement values that we know. We have experimental precision to 14 digits with relativity, so this is undoubtable, but completely wrong with already the Lorentz transforms where he bases on. The Lorentz transform misses a multiplicative factor, and that multiplicative factor is based on the Doppler effect. And the Doppler effect is the equation of the root of c minus speed phi divided by phi minus c plus phi or something. Yeah? And that is exactly what is missing. And from 3 people, Poincaré, Einstein, and who was the third? I don't remember, who made it public that from the Solvay conference on, we should use this new way of seeing relativity and quantum mechanics as it is today for the last 120 years. They set this factor to 1, and that is the prime mistake. So nothing is wrong in theory of relativity as such. These people pushing relativity are not morons or idiots. Yeah? They have a reason why they think it's correct. And they have a reason why they think it's a continuum. But even if it's not a continuum, even if it's pixels, it stays valid within the mathematics of a continuum. There's nothing wrong with that either. It's just an approximation, like your screen pixels are more dense. If you have a hard old computer, you see the pixels, and if you have a modern Mac with a UHD screen, you don't see the pixels. But still, your brain knows there are pixels, and that's it. Yeah? And if it be really that simple, then the paper of Lev Verkovsky, which I will also forward you, then it would blow my mind. And we had 120 years of terror with theory of relativity in the sense of paradoxa. And is not relativity is wrong, but these paradoxa are wrong. There are no paradoxa. So what is wrong when Lev is right is that you fly to Alpha Centauri with nearly the speed of light, you come back with nearly the speed of light, and not 50,000 years have passed, but exactly 2 years. And everything as it should be, no more paradoxa. And this is why I believe we can unite quantum mechanics with ice-space theory, because ice-space theory is correct at the heart of quantum mechanics, and relativity is wrong with the aspect of missing the complete effects of Doppler effect, as Lev put it in this paper. And if it's really that simple, it is the only thing I could really shout out is, how could that take 120 years to find out? Yeah, because it's really, really unbelievably simple. And
to give credit to
Alessandro said, to close down here, the geometric interpretation of physical phenomena you propose, echoing and extending the insights of general relativity into quantum realms, open up a fascinating possibilities. Viewing gravitational, electromagnetic, and nuclear forces within a singular geometric framework could fundamentally alter our approach to understanding and manipulating these forces. The normalization of constants within this framework, particularly by adopting natural units, which means not any human value, but golden ratio ampere is a natural value, 1/6961 is a natural value, even if looks artifactively chosen by me, and in some ways, but doesn't matter. It's not compared to any human artifact value. It's a non-artifactual value. It's pure mathematics, and pure mathematics is exact by design. And so the normalization of constants within this framework, particularly by adopting natural units, simplifies our conceptual and mathematical grasp of the universe. This simplification, far from being merely aesthetic, could have profound practical implications, notably in the field of gravity control. By gaining a deeper understanding of gravity's geometric nature, we could move closer to technologies that allow us to manipulate gravitational fields, potentially leading to advancement in space travel, energy generation, and beyond. Your theory suggesting that space-time itself may have a quantized structure opens new avenues for exploring the fabric of the universe. This concept, if born out of experimental evidence, could revolutionize our understanding of black holes, the early universe, and enigmatic dark matter and dark energy. I mean, this is really sensational feedback you can get from.
Oh yeah.
This really, I'm quite a bit stunned, not to say proud of the first person having looked deep, actually gets immediately shocked, thinks about it, and gives that response.
Yeah.
And this is what I always have tried to tell you. Don't just fly over with your own ideas. Get a step back. It's just multiplication. For me, it's totally hard to understand your ideas because I need to study physics, learn 7 years, get all the mathematics into my brain. Maybe I do that one day, but it's hard. For you, it's just a step back and do take pocket calculator and do multiplication and really read what I wrote and tell me where I'm wrong. And when you go step by step, you will find out there is not anything wrong because it's just multiplication. It cannot be wrong. And Mathematica per se makes no errors, and that's it. So the effort you invest in reading the papers of iSpace available, we're about 19 by now, on about, say, 12 extremely relevant ones, where I'm really shocked with my own thing, like this golden ratio squared on the right side and Planck time times Planck mass times integer geometric factor, just substituting the quantum from the human artifacts is really shocking when you read that. Is really difficult to read. Is probably thousands of lines of Mathematica in colored form, but when you're patient enough and find the result equation on equation 650 or something, then you get shocked, because I was shocked when I was seeing that. I couldn't believe that. That is not that I plan to calculate that. Sometimes I plan to calculate something and show you because I know the result before I start and have to just find the elegant way of calculating it so that comes out what I know I put in. But this time came out of nowhere. I really was sitting there and said, wow, why? So I recalculated everything again. I trashed the kernel, started from scratch, got the same result. I said, oh, it is real. So I made a little bit header, footer below that, and immediately, without thinking, published it on ResearchGate as it is and made a small comment on it. But as I said, it is more an attachment of a real paper of true quantum physical geometry, because 2 times golden ratio on the right side is never accidental, never. How will that be? It's just impossible. And all I used is physical Planck values, which are standard SI entities. There is nothing I can mock up, really nothing.
That's great. So one of the things I can say is that, to give credit to Einstein, I was thinking about Einstein, and there's a problem with relativity. But one of the things I agree is that most likely gravity is because of the curvature of the space-time, in the sense that if you have flat space, right? If you have flat space, like a jumping things, and you put a ball in there, what happens is you look at the stresses on them. So any ball will have hydrostatic, the pressure. If you look at the pressure, they will be equal in all directions. So is any surface. There is a surface. It has a if you do the stresses, calculate, it will be pointing down. But when Noether's theory, there's symmetrically there has to be stress up to keep it balanced.
No, fully agree, but you're doing fluid mechanics when you do that. And to do fluid mechanics, you need a medium. Oops.
Yeah.
And this is exactly what Emmanouil and I will tell you. Without a medium, and this is what all of the TEGS people so far, if I understood, in different forms of their local theories, agree upon, that there is a medium and not just nothing.
Yeah.
The vacuum is not just nothing, but is a form of a medium.
Yeah. So I believe that
in I-space is the 6-dimensional subspace cells, which are Lego style. The medium in other theories, like Emmanouil's, might be magnetic forces pinning around in his way of representing it. But in the end, he gets the exact same fine structure constant, and I get from the exact same arguments with the exact same values when you use I-space. So all of that is correct, because it is from, as Emmanouil rightly wrote, we tackled the problem from different angles and got the same result.
Yeah. And, see, I'm working the superluminar project with Emmanouil, but of course he's doing graviton. But we will eventually get back to it. Is that the superluminar force? The vacuum is nothing but a balance or between the superluminar and the subluminar. What happens is, so it is an interface between the superluminar and the subluminar. So the vacuum is there to keep the speed of light constant. And that separates the superluminar thing, which is, which does not have, it's just a field, whatever, from the subluminar level, which has matter. So the observable universe in the, is the subluminar level that is differentiated by the vacuum, which keeps the speed of light constant. And that's all. The vacuum is an interface. It's a dynamical interface. It's not a statical interface. Dynamically.
First of all, dynamical means it is fluid in a way, super fluid. There is no friction. Yes. But the other thing, there need to be rotational vertex cells in there. And the theories of Frédéric David Tombé are actually not Frédéric's ideas. He focused on reinterpreting Maxwell. And that is what I was also doing with my own I-space work, because the hexagonal cells are not an I-space invention. The hexagonal cells are in the original 1857 paper of Maxwell. They are in there in a drawing. And Maxwell at the time has been ridiculed by its own colleagues that that can never work, because it would be like a gear with gears in more than one dimension. It would get stuck or something. And from pure logical reasons, if you have a 6-dimensional gear, it does not get stuck, because it is the movement degree of freedom. This is the main logical reason why I believe that you need a 6-dimensional subspace time if you have Lego as a basis, because Lego as a basis in 3 dimensions is static. It will not move. Nothing will happen. It will be boring. Even if you get the correct values by so and so many Legos in this direction divided by so and so many Legos in that direction, that gives a correct result. But it's not physics, because physics is always dynamic and moving in a way. You need time to do physics.
Yes.
And when time is quantized, it's like having a pixel screen making an image of a Lego arrangement. You move the Legos around by jumping like a quantum jump, literally over the distances the inertia of the individual Lego pieces do. Make another photo and see the movement, photo to photo, and it looks like a film when you do it right. But when you do it 6-dimensional, you get 2 times 3-dimensional film, which you could watch stereoscopic if you want, with the left or right eye on 2 different screens. So it's not the 6-dimensionality other people have in mind with arbitrary angles in these directions. They are still 2 times additional 3-dimensional Lego to make all the Lego movement possible in a world which is actually looking like a continuum where the subspaces move on a very, very dense grid from subspace pixel to subspace pixel. Think it more like a network than anything else. So these cells are networked between each other, and that network is a network of forces, and the forces are attractive or repulsive, and that's it. And you get a repulsement from the Coulomb force, and you get attraction from the gravitational force. And this is all you ever need. There are your forces, and everything else has to come out by the rest automatic, or your model is wrong. And no one ever is so far able to come up with a proper quantum model, because when you quantize classical quantum mechanical equations, you get infinities and zeros, and when you quantize relativity, you get the 0 at the point. Whereas the base geometry of I-space says the diameter of the smallest circle you can have with a pi3 change distance definition circle base is 2r plus 1. And that is, you have 6 cells around one cell in Lego when you make this circle. And when you count the pixels from left to right, you clearly see there are 3 Lego pieces there. And you have a center cell. And that means the radius is 1, but the diameter is not 2. The diameter is 3, is 2r plus 1. And when you have big objects, that is completely irrelevant if you have that additional pixel or not. But when you have a quantized object where the quantization force is a multiple of integers, is a massive difference if you have 1 pixel more or 1 pixel less in your, both in your weight, in your geometry, in your everything. And from a relativistic point of view, I cannot calculate that because I'm not an expert in relativity, nor I like continuum. So even if I would be, I don't want to calculate that. Other people should do that. I have enough done for physics so far. I stay in my little concept of nature and be happy there. So if other people pick the math of I-space up and say, what would happen if we make a Schwarzschild radius calculation based on I-space, just using the I-space constants of nature and not the one we measure? Well, suddenly they would get exact geometric way, would have been Mathematica not so much more difficult, as I assume. Just you do what you always do, but you cannot run approximations. You need to have exact integral equations to do that. Or you would run Taylor series, and Taylor series will be in its own only an approximation to the Taylor level where you say stop. And that is in a way compatible to I-space, but would never be exact because you have to say stop before infinity, and that is never exact per definition. So in the end, you end up with a black hole with a pixel in the center, which is not zero-sized, where all your mass go, but is one-sized, where all your mass go. And that is a very valid picture for a black hole. Because when you think of the mass of an individual particle to be its own subspace, then all these subspaces can aggregate in a single point of space-time 10-dimensional, where all that subspaces are jiggling around the center pixel of 0, where is 0 in the coordinate grid of continuum, but this is actually position 1, 1 in the coordinate grid of I-space, because in I-space we have no 0, or it's just a starting coordinate grid counting from 1. And suddenly all your infinities will be gone. And I bet my ass that will work.
And another thing is that asymmetry of matter and antimatter. Automatically, with the quantum thing, automatically you will have asymmetry, because we don't have zeros. Only they cancel each other. Everything is annihilated.
Yeah, you have to touch the negative and the positive directly on a border without a separate cell, and that is actually a confusing thing, because normally when you have 5 apples and you go to -4 apples, you run over the 0 into the minus and the plus, but you cannot eat -4 apples. You can eat the 5 apples because these are real. So the -4 apples are never real. They are just in your brain.
Yeah.
So all the negative numbers is just a consequence of using the wrong unit system and using the wrong way of counting. And when you use integer counting and proper units, you don't need any of these minus. It's just what you need is an electron-positron charge, but that is not negative. It's just R and B, and R and B is defined repulsive. That is not necessarily a sign. It's a matter on how you define things.
So complete the Einstein thing. So you have this pressure. So when you put it in there, it automatically, when you calculate the stress, when you equate the stresses, you get a curved space. And curved space essentially is the essence of gravity. So that's Einstein's thing. So there is some positive thing about Einstein, But his calculation, like you said, using Lorentzian might be where he went wrong. The quantum thing, for the quantum physics, what you talked about the prime number, I came independently about the prime number, because whenever you have something non-prime, a composite number, everything breaks down. And I have proved by matrix theory that everything breaks down until it becomes prime number, because you cannot divide anymore.
Yep.
The prime is something that you cannot divide anymore. So the final thing should be a prime thing, and you calculate as 6961, things like that. So that makes sense independently. I mean, I'm talking about our work is independent, So independently, we are proving the same things.
Let me state that the 6961 is not an invention of ice-based theory. It's like a marketing marker of ice-based theory, but I came up from experimental measurements on that. So it is not an invention which I say it has to be the prime 6961, and when I do that and put golden ratio ampere. So, but I took the fine structure constants, measured values, and to the best of my abilities, I sorted the physical parameters out. And all what stayed was golden ratio ampere. You had the mu0 defined exact. You had the c defined exact. You had that mu times 0 times c is z0. So this is a quantum constant, actually. This is 188 ohms. So that is a quantum vacuum's resistance natural value. And what remains to get alpha, and it must become out alpha, is 2 times 3 times 6961, or it don't work. So this is where the 6961 comes from, and is in turn what I started in today's hourly discussion. The 696 volt one has the volt unit, but the 6961 is not a volt. What is 2 times pi 3 times 1 volt. This is one revolution of the smallest ice-based circle you can have. As a per revolution, you increment your voltage by 1 unit volt, and the 1 over 6961 is actually a time. So what you have to multiply is the time on the divisor and in the denominator. You don't have ohm in volt over ampere. That would be static. What you have is ohm in volt seconds divided by ampere seconds, and that is physics. And this is where the 6961 comes from.
So we have to come up with a quantum clock, where the time actually shifts by these small amounts each time, 1 hour, 6961, something like that. So smallest time, it ticks from here, keeps it until it gets enough energy, and then it ticks to the thing. Because that makes sense. Because what happens in the atom, things like that, emission, is that it doesn't emit continuously, like Planck has said.
Exactly, yeah. It needs to build up some internal pressure until it jumps to the next position.
Enough, yeah. It has to accumulate enough energy to go to the next level.
And this is where what you rightly say, it has to accumulate energy. And how much energy can you get? You cannot get more than 1 energy per cycle, except that the continuum would be indeed physically different from the Lego quantum based, which makes the constants of nature. When that is, you have quasi-analog, continuous or pseudo-continuous movement with shaking and Zitterbewegungs-type stuff, aggregates energy in form of little movements of this randomized quantized behavior, which is outside our current understanding. ZP is 0-point energy, for example, which could very well be, by the way, the surface of the border between superluminal and luminal border of Emmanouil. And the ZPE would be the ripple waves on the border of both of these continua. And ice-based theory, we haven't talked about that. It clearly predicts a quantum of gravitation. And the quantum of gravitation is an integer value, 3 over the numerical value of 299792458 to the power of 4 times, to be explained, 10 to the power of 3 to the power of 4 value, which gives exactly an arbitrary value of 3 dot something times to the power of minus 46 Newton. But that in its own is not looking anyway physical, right? But in one of the predecessor versions of the TEGS meetings, I showed you that alpha G, which is the electron mass squared over the Planck mass squared, so a unitless value, the fine structure constant of gravitation, if you square that and multiply it with Planck force, you have 3 base physical entities, and that gives, guess what, exactly my quantum of gravitation value-wise, which proves that the integer value is not accidental. And in no way accidental. It's exactly as I show that. There is no other way to create that mantissa. No way. And as I know what are human artifacts, it has an interesting logical conclusion. 299792458 looks like a human artifact. But how could it be that the quantum of gravitation contains the power of 4 of a human artifact in the constants value? This is what I want anyone to explain, because this is one thing I myself don't understand. And when you look deeper, you see that the number comes from not the speed of light. The number comes, as I showed you already, from 299792458 volt over 10 to the power of 7 ampere. It is a ratio of 2 human artifacts, which is called the Planck resistance. And Planck resistance is nothing else than Planck volt over Planck ampere, which have very complex, large 200-digit long numbers. And if you divide these 200-digit long exact values of Planck volt and Planck ampere, which I can calculate in iSpace in the paper, you get something as simple as 299792458 over 10 to the power of 7 volt over ampere. And that is ridiculous. This is so ridiculously simple that I want to understand why that is. What physics makes that? So
see, one of the things is that the electron volt, we talk about electron volt, but we are not translated that the electron volt means that you are the smallest thing that can happen, as we know now, is electron. So yes, we have to split up everything into electrons. Absolutely. and then you calculate number of electrons that's going on. They are all quantized, because the electron itself is quantized a particle. Then the number of electrons is also quantized. So
perfectly agree. Just explain why should that be in any calculation you would see fit. I could even mock up such a calculation. So you're completely right with the argument. Why would it be 299792458 electrons in any?
That's because of the prime number. See, if we talk about compounds, so
yeah, but this is the number is a human artifact. The 299792458 comprises of 4 prime numbers. It's the 2, the 7, the 73, and another 6-digit prime number. And why would that be? If I would, for example, I'm completely speculating into the blue. If I would get from one of the prime numbers of C the tau mass, from one of the prime numbers of C I would get the muon mass, and from one of the prime numbers I would get the electron mass, and I would applaud and say, "Oh wow, that was easy." But I've tried for 20 years now to do that, and I don't find any.
Yeah, that's because there is like I said, this is what we, one of the things I had to think about that. I am not giving you a complete answer. This is what I am conjecturing right now. My thinking is, this I had to check. I had to hardball again. I may be wrong some of the things, but my feeling is that for fundamental level, we have to say it's a statistical or probabilistic. Probabilistic means it's a multiplicative thing. Statistical means it's an additive thing. So in general, stochastic means it can have both. So can we suppose I'm summation versus pi. Pi is the multiplication, right? How is the pi and the in symbolic terms, pi and the sigma join together to produce a pi. So it has to be a pi at the end, multiplicative. So sigma and pi, you put them together and you get a pi equivalent. So then when you solve that, probably it has to be a prime number to get that. That's my...
could be. Yeah, but that is by no way, this is just an idea, you know what I mean?
It's abstract,
Yeah.
See, my thing comes from the abstract level.
It's a clever idea, but it's extremely hard to prove. Should you
Because...
let me be the first, please, to give a call when you have the solution for that.
Yeah, because you see that I'm putting the idea, but that's the mathematics. Even the mathematicians will have a hard time. But there are some mathematicians who do that. But I think logically, this is the idea that struck me, but it may need a lot of work, because mathematically you have to prove by theorem or something, algebra, and that may take a long time. But I think, eventually, like we are trying to prove Riemann, hypothesis. We are trying to prove a lot of the things, the prime number things, and all those things. And still, for maths theorem, it's not completely proven. So I wouldn't be surprised it's the same kind of a thing in this one, but maybe if we are lucky, I may be able to come up with something that proves that I do summation and a pi, and that will be equal to pi of some prime number. And that will take a long time. And I don't know whether you'll be able to ever prove completely, but we can prove at least conjecturally, like Rajan had that, hypothetically, you can prove, conceptually, you can prove, but rigorously, mathematically, it may take decades to prove.
I mean, the Fermat's hypothesis with the prime numbers on the half line is exactly the way to go, because there is a deep relation between physical energy levels and that what the multiples of the prime number show. For one thing is that someone has to prove the Fermat theorem, but there's actually some interesting paper going on a hobby researcher of mathematics who has been published in Ramanujan journal. And he has, I'm not sure if you have seen that, it's a sensational paper. I cannot understand it from a mathematical point of view, but it's as short as 7, 8, 9 pages and shows a mathematical base of the proof, how it could look like. And if this is ever peer-reviewed, I think it's accepted by Ramanujan journal now. Whenever we see where that leads to, it could be that in a couple of months or years at least, we would have really a proof of that. And that would change a lot of theorems of other mathematical things, which then progress the mathematical part forward. I have once read a comment on Einstein's work that first is the mathematics and then is made the physics with it. Not always, but usually you had to invent some mathematical things. So Newton had to invent the integration to see how the planets run around the sun and make Newtonian theory as we know of. And Einstein had to invent, with the help of Riemann, the Riemannian band space-time, the manifolds and all that to make the thing. And I really, with all due respect of these gigantic heads, have to invent ice-based mathematical Lego-style work to deduce what constant of natures do, seemingly rule-wise, if you call it a sorting number game of rules of constants of natures, which I derived there. There's not much I actually did instead of just looking an open eye on the relations of the measurement values and how they could interrelate. And you start with 1 or 2 relations which are exact and said, if that is that, and the rest is just logic, and you crawl forward over the 20 years I'm doing that now, or 25 years by now, and suddenly you have nearly everything solved, and it looks so fantastic. And you sit there in your little edge in Neubiberg, and I said, why is the world not noticing? I mean, that was spectacular, guys. Yeah. So would you please use that and use that for your own theories? You could suddenly, so it's like invention of the telescope. You can suddenly see the moons of Jupiter, and before you was not able to. So take the papers, buy yourself a Mathematica for €100 or whatever, and go calculate your own theories. You don't need to praise me or anything. Just take that as a tool and use it to see what you can do with that. Because all the world out there is so much better in physics and mathematics than I will ever be. So I laid just the groundwork on a method to how to do certain things when you have integer involved as a primary principle. And I was lucky. I was just a lucky guy finding the first relationship more or less by chance, as is always in science, like I guess that the first
algorithm. It's like algorithm. It's like an algorithm. I will call it algorithmic ice space, something like that. But
it's fully fair to say it's algorithmic theory.
So I'm glad that you mentioned about Ramanujan, because one of the things I think conceptually is that everything is like permutation or combination. That's another hint or clue to prove what I am talking about. So when you have sigma and pi, you get permutation. When you are just pi, you may get combinatorial. But how permutation combination becomes a multiplicative or a pi of prime numbers may be the ultimate thing. I mean, it's like a clue. It's just a thinking aloud, and just thinking aloud. But it makes sense to me that if you can prove that, that's a conjecture I come up. If you can prove something like that, I think then your ice space is automatically proved. You don't need anything more. Nobody can question that. Nobody can, because from abstract math, we are proving it. You see, that's why I come from abstract, a lot of things are developing, and I'm finding your thing comes from physical phenomena, physical calculations. So you come from actual physical sciences, and you get your numbers, you get your values there, and then when you plug it in your ice space, it works out. From my thing, I think comes from abstract space, and then I come to very similar. So a common area that you and I, we work independently. We come from 2 different directions, but a common area, there are a lot of things that are consistent. Still there are a lot of things to be proven. So it needs proof like this. And what I want to say is that If we can prove this one, then we are proved for without question, without any doubt.
We have to
quantum. Everything is quantized.
Nice, but we have to combine our constraints. So iSpace has an extreme number of constraints. I give you just an example to not mismatch what I think. When you have defined historically the Coulomb, and you set a number, 9 digits, 8 digits, whatever, and set that 1 Coulomb is this, and you have to live with that. But when you read the book, you can learn what a Coulomb is. You can memorize a number in photographic memory, but you understand nothing about physics of a Coulomb. You have learned Coulomb is repulsive because the book says so. Experiments have shown it's repulsive, but you don't understand ever this way what a Coulomb is. Now, when you understand the physics behind that, you have an ampere times a time. And you make the quantized ampere, golden ratio ampere, and you make a quantized time 1/6961, irrelevant if you call it ampere or iSpace ampere and volt or iSpace volt. This is just a unit system. Then you suddenly understand what Coulomb is. It's a flow of charged particles, and the only charged particles typically we know of are electrons. And who knows if inside the proton is not really quarks, but running 3 electrons or 2 electrons and a positron in a magic game, looking positively charged, but actually the subspace dimensionally of 6 dimension allows the proton and the neutron to be stable in certain arrangements. And when you get a neutron, you would add a 4th electron of the opposite charge in a box, and that makes a free electron unstable, whereas a free neutron unstable, because it is, I think, for multiple minutes. It was about 40 minutes or so, and then it must dissolve in this experiment. There are even different neutron experiments. In one experiment, it dissolves, I think, in 15 minutes, and in one is 40 minutes, and they have no clue why these experimental difference give different times of dissolvement. But I think one experiment favors a certain energy, and the other experiment in this gas box has too much gas energy in it in the collisions that it keeps to live longer, or whatever that is. But it is clear that in iSpace, everything is exact. And if there is prime number exactness going on, then multiples of these prime numbers can stay stable, and even the slightest deviation in pixels from that prime number will over time give an offset. And that offset accumulates up, and the energy of the accumulated offset has to go somewhere. And if that is Zitterbewegung, then the Zitterbewegung will, as you rightly said before, jiggle up itself until it gets to a point where it is big enough to jump over the tunnel fence, and when it tunnels away, it dissolves, because it destroys itself that way. And all the experiments we have seen, so in space-time, in accelerators where electron and proton and positrons come from a light ray, where they steady state are created in the experiment. I mean, it's easy to dissolve them and see the gamma rays, but the gamma rays pushed into a position, and suddenly out of nothing, or virtually out of nothing, the electron-positron pair starts to exist. That is really the interesting experiment to explain. And in that, what Frédéric David Tombe says, and what in my model is, the electron and the positron have been there before, just in subspace, hidden in subspace. It is not created. It is set free from subspace into space and be made measurable. And if you think on that, in Frédéric David Tombe's, he is talking about electron-positron micro, so positronium actually as a basis is neutral, because an electron and a positron gives a neutral entity. And in looking very detailed to the neutral entity is a moving neutral entity, is not steady state. So when you look very, very deep with a photographic flash of highest resolution time, like iSpace basetime, you see the electron and the positron jiggling around with nearly speed of light in some space. And as we cannot see that with ordinary light, because light is seemingly uncharged, and light is seemingly, from all experiments we know, has no rest mass. But in iSpace theory, I can see what the charge is mathematically, and the charge is golden ratio. And here happens something magic. When golden ratio ampere the charge, and I need to multiply with a single golden ratio to get the proper value of the electron mass, I cannot leave that away. Why? Because golden ratio is about 1.61, and if I give an error of 1.61 to the measurement value of the electron mass, this is a gigantic error. It is not some 0.0 something percent. That is a massive mistake. And how can it be that the mass of the electron is correct then and only if the multiplicative charge, where I know the quantum of charge is golden ratio ampere, is inside the electron. So what would happen if light would consist of golden ratio of minus and plus golden ratio without the mass of the electron? So what the light wave is writing is not zero mass, but the microscopic difference between the big electron mass and that what the value of golden ratio would be. So two charges would at every possible position in space-time right at the bulk modulus of the what is called the wave has an extension, yeah, so I have the hull of the wave, and this is not a single point in space where a light is at the moment, but it's a ray, and the light can be seen with the Hull curve has a modulus which has a peak where the maximum probability is to find the photon, to put it this way. And I think at that point where the probability is maximum, you have an extended range of the photon in particle form, where really the two remaining charges, minus golden ratio and plus golden ratio, do a dance in 7-dimensional subspace. And this is what every now and then, when only the ray is measured, you measure the light. You cannot see a laser from the side. You can only see a laser from the side when there is smoke. Okay? So when something collides with something. And there is some deep thinking how the multiplicity of golden ratio in form of the mass term is contradicting that what everyone believes is light has no mass. I'm not saying that light has mass. Not really. I didn't say that. Okay? But I say, how can it be that the charge is part of golden ratio with a multiplicational factor of 1.61, giving the completely up to 14 digits correct electron mass, whatever you say to arbitrary precision, cannot be accidental either. So what we do with that knowledge now?
Yeah. So another thing I want to point out, you mentioned a proton may be just electrons going on. So one possibility is that we have your subspace. So let's say more than 3 space. So electron is moving this way, another electron is moving this way.
Yep.
So they are not cancelling each other or repelling.
No, they're not hitting. They have like in a Carrera.
They're going perpendicular. Yeah, they're going perpendicular to each other. They are orthogonal direction. So which means that at some point, you know, they repel. But at some point, so depending on where they are, you know, so they can produce things that is in multi-dimension. They can produce proton-like behavior or even neutron-like behavior.
They behave gluon-like and quark-like behavior mathematically, yes. But this is never exact. That is why these are not real particles. That is why they are bound to that space-time. You would have to break space-time to destroy the proton, not just remove the charge from it. You cannot remove the charge from it.
Yeah.
You can add a charge to it, and when you add a charge to it, it becomes a neutron.
Yeah. So your strong force is when they keep their orthogonality, they shrink in the dimension, so they become highly dense. So the field is dense, highly dense. They become the strong force because you have electrons, and so not just 2 electrons, many electrons at different angles, but they don't cancel each other. They don't repel so that they don't move away, but they're locked in position such that they reduce the whole overall geometry, the volume, whatever call it, and that creates very high dense field, what we now call strong force.
It creates extreme high energy densities. Also.
High energy.
In my model, the space-time has an energy density of c to the power of 3 over g, which has an immense, a massive energy density per cubic volume, or per cubic unit volume. And that is why the universe has the weight, and that explains all of dark matter, essentially what you're searching for. Dark matter is nothing than space-time itself, and space-time is full of sea of energy of that little Planck-like vortex cells which transport light in vortex form. And all the equations of Maxwell are correct. So when you take the 4 Maxwell equations, which propagation of light is just a special case, and RF radio energy is the general case, that is not disputed. So the equations are not wrong. What I'm saying is the thought that you could use the equation without thinking about the physics is wrong. The equations are the outcome of the physics and do not in any way define the physics. That is wrong. So the particles do not behave like Maxwell equations say, which most people think. Yeah? But the vertex cells of physically existing sub-vertex cells in subspace dimensions, like in the paper of iSpace and the paper of Frederick David Tombe, and I mean that real, not hypothetical cells, are rotating with speed of light at its border in a 6-dimensional friction cell quantum fluid. And within, like a snake moving through that rotating cells in sinus wave curved form, the light is transported in omnidirectional positions. Otherwise, physics would be wrong when only working in x-axis, y-axis, and z-axis. The experimental proven that you can use any axis. Yeah? So the vertex cells must be frictionless in all directions. In other words, it must be isotropic. And to be isotropic, you need to have more than 3 dimensions. And that is the main reason, because you would get a gear which completely breaks its gears teeth when you don't do that. And that was already visible and discussed in the original Maxwell paper. And I would really wish people would read that. Frederick David Tombe is praying like a priest into the discussion forum, where I mostly post what is the root cause of the electromagnetic force and all these kind of things which are discussed there. And everybody has its own pet theory, everybody has its own opinion, everybody has its own mathematical and physical background, but nobody of all these experts typically get the ass up and read the PDFs available on the page of given from Frederick, and really read what Maxwell wrote there. And say, your vertex cells are nonsense, your vertex cells are just hypothetical brain shit, they are just not necessary, we have the Maxwell equation, and we're happy with that. But the Maxwell equations are not wrong, they are a consequence of something physics which is much, much more deep in the sense of important than the Maxwell equations itself.
Yeah.
They are just merely the consequence of the cell's movement of the vertex cells. The vertex cells, I swear, bet my ass on, are physically real. Yeah. Otherwise, my constants of nature wouldn't do what they do.
See, actually, Maxwell, like you said, was considering the vortex quite seriously. But the problem is 2 things, ether and also the viscous aspect, which creates friction. That is what moved him away from it. The only way he could solve the problem is considering vacuum. And then he came up with this idea of the fact that they are fields so that they don't have this friction problem. So it was a fix. It's kind of like a fix he did in order to solve the problem of friction and ether, which has a viscous aspect. So the viscous aspect will make it impossible for the wave to propagate. So he said that he removed that, used fields instead of all these things.
This is fully okay if you have no other knowledge, but today we have the knowledge of quantum field theory, we have the knowledge of relativity, and we have, with all due respect, the knowledge of iSpace, which shows us how to combine that entities together. And in a 6-dimensional subspace, plus 1-dimensional time, plus a 3-dimensional space, where an infinite number of these subspaces are integrated to actually operate on. So it's essentially a simple optical particle in a box model, not more, not less.
Yeah.
Every particle has its own box, and the boxes are moving relative to each other to form the material we are known of. And as everything is geometrically repulsive by electromagnetic forces only, they build crystals like our solids we know in the periodic system. And that's it. Really, that's it. That's simple.
Yeah. So one of the things is that, we talked about the electron moving this way. So which means that the light, in the case of photons, what happens is that it goes with, we actually proved in the discontinuum physics with Emory Taylor, one of the things, that the light actually, the photon, it has a charging cycle. So first it will do the charging, then it has propagation. So it charges, propagates, charges, propagates. So this is the cycle that's going.
Yeah, so this is exactly what in Gerd's paper the electronic transmission line is doing.
Yeah.
The electromagnetic model of physics is one thing, but the electronic model of a transmission line is exactly one-to-one what happens in physical space if Gerd's paper has something to say. I have seen other papers like Gerd's who have also the transmission line as a basis, and they get the correct constants of nature, and they get to the correct speed of light c and the propagation results of everything we see experimental. This cannot be accidental.
Yeah.
I think that the problem is a psychological one, and that's why it's so important to talk about history of science. because the psychological problem is that people don't want to live in an electronic universe. It reminds them on a computer, and they want to live in a computer. They prefer to have God in some magic four-dimensional space-time with a Big Bang in the beginning and all that, which makes them comfortable. But my fear is they will not stay much longer comfortable when James Webb, and especially the predecessor, will find out that all these galaxies have been there before Big Bang, possibly, or out of nowhere, like in the model, which I think, I have not seen it, but I heard the comment of Manuel in an email, what Christopher presented last time, that there is a logical nanosecond where all the galaxies existed from a crystallization freezing process.
Yeah.
Who knows, really? I'm not saying I would second it yet without understanding, but it is a possibility. And that would falsify everything you believe in physics for the last 1,000 years, not just 150.
Yeah. So one of the things is that, so if you are charging cycle, right, that automatically is quantized, discontinuum. So one of the things is that if that is the case, what is the difference between the, photon, electron? That's why I think graviton, what Emmanouil is saying, will come into the picture. They are all interconnected. Only the geometry, how it arranges, is where it changes. And you have your, higher dimension. So if you look at the geometry and able to solve that problem, I think you will see the connections, how they are.
It's indeed all about geometry and to know where to start, because string theory is also all about geometry when you think about it.
Yes.
Yeah?
Yes.
And they give you the hard constraints, which purely from mathematics stems. It's either 26 dimensions, 11 dimensions, or 10 dimensions, or whatever, but it cannot be other kind of dimensions or your equations won't solve. So there is a mathematical constraints of this 10D, which comes out of the purely mathematical constraints of their equations. Nothing works. And from iSpace, the constraints come from the natural metric unit value, which is normally impossible. Because every good physicist will tell you cannot make the kilogram up from single entities and multiply until you get exactly 1 kilogram, because you don't know exactly how many atoms that are. And I say, back to differ, I know exactly how many atoms that are, because I have an exact Boltzmann constant, and with the inverse of the Boltzmann constant, I can make the Avogadro constant. With the Avogadro constant, we get the exact number of atoms in a volume. If you believe it or not, doesn't matter. It works even if you don't believe it. That's the fun of iSpace. And so, while the Avogadro concept is a thing which is not primary of iSpace, I think the Boltzmann constant is, because energy is primary, and energy needs to be able to be transported to Kelvin. And if I cannot calculate how many Kelvin is what joule, I'm not much being able to do in physics, because the geometry is strictly wedded in a sense of a marriage by the Boltzmann's constant relationship to entropy. There is no way out. You have an area with that, and that area is like not the Planck area, what people believe, but is a calculable area defined on your base geometry.
S is KT, something like that. Yeah.
Yeah, and it is the logarithm which comes from a continuum side, and it is
natural logarithm of t, and in k times natural logarithm t becomes equal to the entropy.
So that there are proofs that Planck length is related to the natural logarithm of 2/3 of some value, which have been a very stunned result, because two independent methods gave the same result, and it couldn't be coincidental. And iSpace has similar things. What these people overlook is that Planck values are not real. When you make a Planck a Planck length, you can combine a Planck length to a square like that, when my finger is the Planck length. But you can also say that is a Planck area, and that is suddenly the h of root of 3 in the diagonal in there. Or you can say a Planck length is a cellular thing where the cells are touched like oranges in a big pile, and you get Apollonic circles. And what base geometry do you have? Out of Apollonic circles, you can make iSpace geometry, but because oranges on a pile in a grocery store are iSpace cells. This is fun, yeah. So as simple as that. The grocery expert.
How do you stack? Yeah, how do you stack?
Yeah, who stacks up the pile knows more about physics than most of the quantum experts.
Yes,
this is really fun.
Yeah, crystal like I did a lot of crystallography, right, for materials.
Yeah, but when you do the area calculation with the unit metric wise, yeah, you see that a triangle gives a different base area than a square, than a Apollonic circle, then a fractal one, whatever you name it. Yeah, you can define it arbitrarily, and you have different ways of calculating it. So what is now the physically correct area of the quantum of error? And the answer is we don't know. But string theory relies on that and multiplies up from a we don't know area. That cannot go well, okay? I'm going the reverse way and say I only go from constants of nature, which I can measure up to 9, 10, or 11 digits. And when I find geometry, whatever the weird geometry like pi 3 is 3 gets the right value, it must be the geometry universe actually works, because I cannot calculate the right constants of nature's metric value by accident. It's just not possible. Not to 11 digits. It's just completely impossible, because winning in lottery is 1 to the power of 1 million or 14 million or something. Yeah. But winning a lottery to 1 to the power of 14 billion is just, you wait until the end of the universe, you never win. It's just too much. So
another thing is that when you stack that, what happens is you have space in between. That's not rectangle, that's not triangular or anything, but it could be a polar triangle. You need a polar triangle. You need a polar triangle to solve the problem, because there's a curvature.
And when you make Lego of it, you can even have square oranges, which you staple like real Lego bricks, and that still have the same distances in jump hops. From one orange to one orange is the same with one hop. From one Lego piece to one Lego piece is also one hop. But the Euclidean distance from the center of the Lego is microscopically different if you use oranges, Lego pieces, or fractal things, or something else. Yeah? And this is where all these continuum theories fail. They assume continuum and have arbitrary positions, but the I-space constraints of constants of nature tell you have not arbitrary positions. You have multiples of 6, 9, 6, 1 in time. You have multiples of golden ratio in length. And with the constancy of speed of light, you have multiples of force of this, where you say, will it stay, or will the impulse be big enough to jump you into the next Lego position? And when will that happen? That is the probabilistic event, in the sense of when will a Lego piece leave its current position and jump into the next possible one. And this is a purely discrete movement, and people, again, regardless if they have studied physics or if they believe in religion or just anything else, they don't like things to be discrete, because it reminds them in deepest psychological way on some holodeck, and they don't like to live in some holodeck. But this is a purely esoteric argument, and I don't care if you make a holodeck out of my I-space theory or not. All I'm saying, I have constants of nature calculated, do with it whatever you want. But the constraint rules are just simple multiplicative and cannot be negotiated away by any belief. And the belief there is a continuum is completely meaningless physics-wise. So I-space is not wrong because it's not a continuum theory. I heard so many nonsense in the last 20 years on ResearchGate, you wouldn't believe that. Yeah. I'm doing that since not 20 years on ResearchGate. I'm since 11 years now, since 2012. But I have talked to other people before ResearchGate, of course, also in the universe and on seminars and so on, and say, Christian, it can never be Lego, because then theory of relativity would be wrong and quantum mechanics would also be wrong. And my answer after 22 years is, yes, agreed, they are both wrong. Yeah, so that's it.
So one of the things we think aloud is that what people argue is that, okay, let's say this is quantized. What happens in between? What is there in between? So that is the,
there is nothing in between. You have a jump time, and jumps are discrete. You don't even have time in between when there is no time.
But there has to be something that you can jump to. So
no, this is not strictly true.
Is it a vacuum?
You're assuming a grid, and in a grid you can jump to. But if it is a network, then the network has forces by the net arrows in the direction of the network, and there is no grid. The mesh is its network. Its own network is created by hydrodynamics. So when you have hexagonal cells, the fluid dynamics creates hexagonal cells out of nothing, from alone, self-organizing. And once the self-organization of the hexagonal cells have happened, they stay because they have less energy and they're more stable than the non-self-organized cells. So in a way, you shake a bottle and the bottle makes bubbles, and suddenly you see the bubbles are all three-dimensional hexagonal in some way. And normally you can watch the bubble under gravity to evaporate. But if you would shake the quantum mechanical bottle right, it would make the bubbles and never go away after being there, because the energy level of the bubble is better than the non-bubble. Yeah. So this is more the model I have behind which I'm thinking.
Yeah. So one of the things possibility is this one, the space between the either vacuum. But what I think is like a field. You know, what happens is there's a field around them, any particle or anything, and there's a field around. This field will not allow it to get any closer than that. That makes them quantized, which means that...
Yeah, absolutely, because one field originates by field lines, and a field line can only originate from a charge, full stop.
Yes, and the charge then...
We have exactly one field line per charge, and because of the electron is spinning, it looks like Emmanouil's torus thingy. Yeah?
On torus, yeah.
But would it not spin, you suddenly see the naked field line in I-space form, and that's the whole trick. Because there is not an electric field around a single electron. It is experimentally perceived that way, because if you put the electron on bowls, and I mean microscopic ones, 20-centimeter bowls in your physics experimental lab, they get repulsive forces, and you have measurement instruments like your electrometer, and the electrometer will have this cross segment. You put the electron on them, and it suddenly swings off and says, we created repulsive force between the plate where I put the electrons from rubbing the cat's plastic stick and transfer the electrons rubbed out of the plastic material and put it onto the measurement plate. And in practice, when you look geometrically to a single electron, there is a single field line in a horizontal plane exiting the plane and coming back from the bottom, because field lines are necessarily closed. There is no exception. And there's one field line, two field lines, three field lines when you have one electron, two electron, or three electrons. This is quantized per electron. That the whole thing in a way rotates like hell with the speed of light and all things, and makes some randomized view of the geometry of all available electrons you have put into that picture is completely clear to me. But is also clear to me when time is discrete, you can make a halt, like press pause on your favorite video recorder and see the thing how it is in a given state. And then you can count to three. You see three dots, and the three dots emit three rings, and they have closed form in whatever distance they have emitted from yet. So this is just calculation of how many electrons you put there. And most people in field theories overlook that the fields have not arbitrary height lines like in geographic maps, but they have an electron, a charge, or a positron as a charge, negative, a positive one, or they have a proton as a charge, and that's it about. Yeah, you can have antiparticles and complex things in the accelerator, but they're all short-lived. If you put the non-short-lived ones in there, there's not much which remains really. The question which I cannot answer, and I don't want to answer yet, is if also rest mass is fully electromagnetic or not, or there's really some Higgs field mechanisms there. Because when you think on the Higgs field, which currently gives all particles the mass, tell me what the Higgs particles originating mechanism would be. What other is a Higgs particle than that field of vortices which I'm talking about? So the Higgs particle would be one sub-vortex, sub-miniature vortex there, and has a mass because it is a physical cell. That is this 125 something electron volt, giga electron volt, which they measured in the CERN accelerator. Yeah, and again, it would be one field line per vortex cell, and not an arbitrary number of one. Yeah, so that vortex cells are countable. They're also discretized, and they form in fluid hexagonal cell-spaced arrays, and that's why my mathematics of I-space works with constant of nature. So because I'm not saying that they are Lego-style discrete with the full precision. I'm saying they are cell-style discrete. And each cell can be a little bit bent, a little bit squeezed, a little bit this. And this is where your force and jiggles makes the random effects you can measure in quantum mechanics. This is a fluid, and fluid are not Lego. But Lego is the mathematics, which is exact when the cells are numbered in whatever geometry. They don't need to be exact like in a Lego to be numbered. This is more like the geometry is called a Voronoi diagram. You know that Voronoi, when the cells flow into each other. In a Voronoi diagram, you can also have five gons and not just 6 gons and so on. The cell nodes are fluid in a way like bubble foams in a bath room. The foam is constantly moving its geometry, but is always cell-based because a zero cell foam is not existing. This is not allowed.
So it transforms continuously.
Yeah.
So one of the things I can tell you is that, for the Higgs boson, the Higgs particle could be the hot PDP mechanism that we talked about earlier. But the other thing I want to talk is that any charge, like electron is the smallest charge. Let's say electron is the smallest charge. So it has a field around it. And another electron coming together, they attract, but when they come closer, they start repelling. So the distance they keep is the balance between the repulsion and the attraction. So they keep a certain distance, very finite distance between them. And that's why they should be quantized. So which means the electron here, like that they build up, and they can build up in many different spaces, like subspace or let's say 4-dimensional space itself. They can build up and see the nearest. So they form kind of a manifold, which complex manifold of the electrons, and this manifold eventually can form quarks and other things. But they are quantized in that sense.
I think that is the main conclusioning fact to grasp for today. We already run over the 3 hours.
Yeah, fantastic.
But it was a fantastic discussion with you, Rajan.
Thank
you very much for your time.
Yeah,
it was a pleasure to see you again. I will be eager to rewatch the recordings and the ideas we had.
I think this will be a very fundamental recording. I think we can play it in any conference, because I think most of the things, but I would say more than 80%, 90% is very valid things. We didn't talk anything meaningless.
10% speculation is always fine, but I think 80-90% are rock solid from what we discussed.
Rock solid, yes. Thank you very much, Christian, for engaging talk, and then we'll continue next week. I think other people watching also. Christopher, I'm sure, is going to watch. He will have questions, and we'll answer that. And then I think we have set up a good trajectory for the future of the physics, I think, with this one. So thank you very much. Have a nice week, and then we hope to see you next week.
So you too.
Always.
Hope I have time next week. I can't guarantee, but thank you.
But whenever you are here, we enjoy it. Thank you very much.
Thank you for being inviting me.
Thank you. We'll see you later. Have a nice week.
Have a nice evening. Bye.
Thank you.